Okay. Okay. Well, this is a little bit easier of a room than the one we have at G11. Thanks, Juan. We're going to cover another really exciting topic that has really occupied many people and that's still occupying many people in the design of especially today's systems where you have memory that's shared across many, many cores. And that's going to be the topic of memory interference and quality of service. This will really occupy us for the next few lectures, I believe. Today we will focus mainly on memory scheduling to minimize memory interference, and we'll look at different problems related to that happen when memory is shared between multiple different threads or cores. And quality of service is very intimately related to memory interference. Whenever you have interference, you have a problem of quality of service. I'll use Tannin bar as one of my favorite examples, right? Remember the bandwidth bottleneck when you're entering Tannin bar, the coffee shop? Well, if you're behind a group of 100 people, you really experience a very high amount of interference, right? That's exactly what's happening in a memory system, in a multi-core system today, actually. A thread can generate 100 requests, another thread can generate 1 request yourself, and you get denied service for a while because a group of 100 people need to go through that revolving door. So how do you provide quality of service in that case? Well, maybe you take one from this group and one from this other group. So one person out of that 100 goes first, and then you go next. That way you get some quality of service without degrading the quality of service of that 100-person group by much, right? So that's exactly the same problem. And we're going to talk about that. But of course, memory system may be more complicated than the single revolving door. As a result, we will see a lot of other issues. Okay, this is just a reminder of what you've been doing. We've been looking at control dependence handling, branch prediction, trace caches, and other methods of control dependence handling. We covered actually in the last 2 weeks. So you're really up to date on what's going on in control dependence handling in the last 40 years, if you will. Well, more than 40 years, actually, because if you remember, the fine-grained multi-threading ideas were from 1960s. It's almost 60 years, actually, today. Okay, and we also covered other mechanisms for predicting other branches as well. So in the next few lectures, and today, we're going to talk about resource sharing in multi-core systems and talk about the memory interference and the quality of service problem. Focus a lot on memory scheduling today. I'll give you actually a very recent overview of focusing on a lot of the works that we have done. So hopefully this will be very interesting and exciting. And then we will, if time permits, we will move to other approaches to mitigate and control memory interference, because scheduling is not the only approach. You could actually partition the memory banks, for example, or you could try to throttle the sources. For example, these 100 people, you could tell them, wait, you're not going for a while. Let the other people who have smaller batches, if you will, smaller group sizes go first. That's throttling, right? That's throttling that big groups. So that's another way of handling interference as opposed to scheduling. And we'll see other techniques. Okay, so this is some quick summary papers. I don't expect you to read all of them, but some of them will be required as part of your reviews. I don't know which ones yet. But we'll cover a lot of these, actually. Okay, but let's talk about the problem. This is a picture that I put up earlier in the past. And in the past, I said that most of the memory system is dedicated to moving and storing data. And also, it's a shared resource. If you look over here, other than the cores, everything else is shared across the threads executing on those cores. There are shared caches, shared interconnect, other shared caches, shared memory controllers, other shared interconnect, shared memory, ... And the disk, of course, is shared. If somebody tells you disk isn't shared, you could tell them, what are you smoking? I'm saying this because this is a review we got from a major conference. We were actually tackling the problem of quality of service in an SSD, and somebody says, are disks shared in existing systems across applications? Well, I'm not sure. Anyway, it's a bit sad, sorry. I had to do this. But everything else is over here, other than the cores, is shared. Well, in cores, you have private caches, private register files, of course. Even those are shared, actually, if you think about a multi-threaded engine. If you have multi-threading, multiple threads executing within a core, even the L1 cache is shared. Okay, so why do we do this, basically? We're sharing resources because dedicating a hardware resource to a single hardware context, single thread, or single process is expensive. As opposed to that, we're going to allow multiple contexts, hardware contexts, or threads to use it. And example resources may be functional units, pipeline, caches, buses, memory, ... In fact, in multi-threaded pipelines, functional units are shared across different threads at the same time as well. So why do we do this? Because it improves our utilization and efficiency. It improves throughput, because when a resource is not being used by one thread or one process or one application or one virtual machine, you can actually expand this. But I'll use the concept of thread because it's the minimal concept that we have at this point for a hardware context. Another thread can use it, and there's no need to replicate the shared data. That's another benefit over here. And it also reduces communication latency because, for example, if you are sharing data between different threads, you can keep all of that shared data in the same cache in a multi-threaded processor. SMT is simultaneous multi-threading. We may cover it later on. So these two are actually big benefits because you don't need to replicate the data across different caches, for example, right? And also, it's compatible with the shared memory model because that's what we're talking about over here. If you're sharing data, you're really sharing memory across threads. Of course, these are good advantages. Today, in many systems, it's used for improving utilization and efficiency. For example, you could think of this concept at a much higher level than processors as well, right? Data center. Do you dedicate a huge cluster just for running, let's say, a mail server? Or do you actually share that huge cluster between a mail server, a database engine, I don't know, video serving engine, ... right? If you're Google, for example, you may be sharing your big data center between many different applications. That's good for improving utilization and efficiency, even though these benefits may not be there. Right? So resource sharing is, in general, good for improving utilization. The downside is it results in contention for resources that we've talked about. For example, Tannin bar has a single revolving door, right? They could have replicated those doors, but for every single person who's going to enter, but that's very expensive, right? So they improved utilization, but then they cause contention. So when the resource is not idle, another thread cannot use it. You cause one thread causes interference to another. And this is true for the space as well. So if you think about this, this is really about time or bandwidth. When the resource is servicing someone else, you cannot service someone who needs it. And also, if you have storage in the resource, if the space is occupied by one thread, another thread needs to reoccupy it, basically. So this is true for a cache, for example. If you are occupying a large chunk of the cache, if another thread needs it, too bad you've occupied it, so another thread needs to displace this thread's cache blocks. That's true for the SSD, that's true for main memory, ... So as a result of contention, resource sharing sometimes reduces each thread's or some threads' performance, depending on how you do the resource sharing, or all threads' performance, sometimes in the entire system's performance. And thread performance actually can be worse than when it's run alone. In fact, all systems' performance can be worse than when it's run alone if this is not correct, this is not done well. And there's another downside, it eliminates performance isolation, because if you always have the resource that you need, the same amount of resource that you need, you know what to expect in terms of performance you're getting. But if your performance now depends on the contention that's caused by other threads, which may change depending on when you run the program, you now can get inconsistent performance across runs, right? And that could be a downside, especially if you care about the latency or bandwidth of your program or a request, right? So that's one downside. For example, if you put a video server together with a mail server and many other things, the video server has strict latency and bandwidth requirements from the user. And if you don't guarantee that in your data center, in all of your resources, you may actually get unhappy customers. Okay, so thread performance depends on the co-executing threads, other threads that are running, and their interference patterns. And we're going to look a lot into that today. And clearly, uncontrolled, free-for-all sharing degrades quality of service. Quality of service can be defined broadly. here, performance isolation is a very strict form of quality of service, for example. But quality of service may also be that your job takes much longer, right? Maybe you don't require performance guarantees, but it causes some discomfort to someone. And I'll call uncontrolled sharing as free-for-all sharing, meaning that if a thread demands a resource, it gets it. That's basically called free-for-all. Okay, this causes unfairness and starvation. This may make scheduling also harder. For example, if something starves, how do you ensure that it doesn't starve? Starvation is in general not good, right? Because people run jobs so that they don't starve. And unfairness is actually, if you're unfair to different jobs, that may actually lead to long-term quality of service degradations as well, even though in the short term it may not matter that much. Okay, so basically, if you're doing the sharing, you need to really efficiently and fairly utilize the shared resources. And I'll give you an example. This is slides used from this paper that was published a long time ago, 13 years ago. Basically, if you have a shared cache and if you have two different applications, let's assume this application, this thread, occupies part of the shared cache. And then later, it requires this much of the shared cache if it's running alone. And this other thread requires this much of the shared cache when it's running alone. When they run together, it turns out that this thread occupies more of the cache. Basically, it gets its share almost, whereas it's not allowing the other thread to get its share because we have free-for-all sharing. As a result, this thread's throughput is significantly degraded because we have unfairness in the cache. Why might this happen? Well, it might happen because this thread actually has a large working set, and it just occupies that large amount of cache, right? This might also happen, actually, if this thread is streaming through memory, even though it may not get benefit from the cache. Assume that you're streaming through a billion cache blocks. It may not get a lot of benefit from the cache, but the cache is allocating a billion cache blocks over time. And this thread has a smaller working set size in the L2 cache. Even though it has very, very good locality and would get a lot of benefit from the cache, its blocks are getting displaced by the a billion cache blocks that are brought in by this thread. As a result, the performance of this thread tanks. And the performance of this thread doesn't benefit because it doesn't really benefit from caching if you're streaming through a billion cache blocks, right? So if you actually have unfair cache sharing, you may degrade overall system performance compared to when you run these different things alone. Okay, so that's hopefully a good example. And there are many, many interference patterns. And this is just two applications, as you can see, right? If you have 16 different cores sharing a large or small L2 cache, then you have a bigger problem. So we'll get back to caching in the next lectures. We're going to focus on the memory problem, which is a bit harder to solve, in my opinion, in this lecture. So, okay, I hope I've convinced you that unpredictable performance is bad, but I'll talk a little bit more about it. If you have unpredictable performance, you also make programmers' life difficult, because an optimized program, you may be optimizing your program really well, like for cache locality, but you can get very low performance in the end because your cache is unfair. It doesn't care about your locality. It basically allocates resources to whoever demands it. And whoever demands it, someone else may not have optimized their program, or maybe it's hard to optimize their program. They're just streaming through memory, and they destroy the performance of an optimized program. So basically, performance optimizations may become useless in that sense, right? So that's a big downside. So you really want some predictable performance such that the programmer can make assumptions as to what to optimize for. Okay, it clearly causes discomfort to the user. An important program can starve, and this is true not only in hardware resources but software resources also, right? If you do software scheduling, for example, at the operating system level, a very important concern is to ensure that interactive programs are scheduled early so that the users can actually is actually comfortable. Right? There are many other shared software resources also. Locks, for example, at some point, long time ago, I think this has changed to become much better. Long time ago at Microsoft, the different programs, Excel, PowerPoint, Word, they used to have a shared access to, I believe, the storage medium. And they actually shared a lock. So when one of them was paging in things from the shared storage, the other one was being delayed. So this is a problem of shared software resources that are not being managed well, because when I'm using Excel, I'm doing something, I should not be bothered by what's happening in some other application, like Word, right? But if you have a shared software base for all of those applications, then you may have a problem. This is old, of course. Okay, so on top of this, this makes system management difficult, because if you're a data center provider, for example, and if you promised a service level agreement to someone whose code you're running in your data center, how do you enforce that you can satisfy that service level agreement when you have uncontrollable sharing in the hardware resources or the software resources? When your cache is, for example, being thrashed by some other workload? Well, if you don't have support for fairness, what you may do is oversubscribe, meaning buy a lot of machines and dedicate that machine to that particular application that you promised a strict service level agreement for, like a latency guarantee. Now, there's a clear problem with that, right? Your cost increases, your power increases, your energy increases, ... So clearly that goes back to dedicated resources as opposed to shared resources. And this has been the case in many data centers today. They're actually over-provisioned a lot to satisfy some of these strict service level agreement guarantees for different applications. But they don't want to be over-provisioned, because over-provisioning is bad in many, many dimensions in terms of cost, power, energy, area, cooling, anything that you can imagine. So if you can guarantee service level agreement while sharing hardware resources, that's much, much better. And today, actually, many data centers, initially, a lot of data centers were not shared between different applications, but now people are moving toward consolidating many, many applications in data centers. So as you can see, I'm using the resource sharing concept at different levels, right? In the data center, you have the resource sharing concept, and also at the very low levels, you have the resource sharing concepts also. Okay, clearly sharing improves throughput. It gives you better utilization of space and bandwidth. But partitioning, or dedicating a resource to a particular application, let's say, provides performance isolation, because it gives you dedicated space and dedicated bandwidth. The key question that we're going to try to answer is, can we get the benefits of both as much as possible? We want to keep the throughput and utilization and efficiency benefits of sharing while trying to do a little bit partitioning or control of these resources. So the idea is basically to design the shared resources such that they're efficiently utilized, controllable, and partitionable. And hopefully we won't waste any resources this way, and we'll have quality of service mechanisms for threads. Because if you actually partition, you waste a lot of resources. Again, think about having 1,000 revolving doors to enter Tannin bar, right? Not only costly, even if you do it, you waste a lot of resources, because you don't have 1,000 people entering Tannin bar every second. Okay, so let's look at the shared hardware resource. I said almost everything is shared, but to be more concrete, memory subsystem is shared in both multi-thread and multi-core architectures, all non-private caches, all interconnects, clearly memory controllers, buses, and banks. And we're going to focus on this one to begin with. The I/O subsystem is also shared, which we're not going to talk about as much, but it's essentially a very similar problem. Storage controllers, DMA controllers, Ethernet controllers, ... And even the processor is shared if you have multi-threading in the processor, like L1 caches and the pipeline resources. And there are many proposals where you want to do register sharing as well, but we're not going to talk about that. Okay, so this is the memory system more concretely. Any questions? Things are good? Clear? Okay. Everybody's convinced that this is an important problem? Okay, good. I hope you have personal examples of this problem also in your life. I always have this problem in my computer, for example, but I'm not going to complain about that. Okay, so basically this is an example multi-core system. Threads requests basically interfere in this shared memory system, and we're going to focus ourselves to this shared memory system. And this was my picture before. The problem is threads share the memory system, but the memory system doesn't distinguish between threads requests. And this has been the case initially when multi-core systems are designed. Today, we're actually at a much better place, and we'll talk about that much better place later on. But let's assume that this is the case. And in many existing memory systems, you may have free-for-all resource sharing, where resources are shared based on demand. And control algorithms may be thread unaware and thread unfair. As a result, aggressive threads can deny service to others, as I've shown you. And the memory system may not try to reduce or control inter-thread interference. And you remember this picture that I showed you in the past, right? This is actually data that we had collected when multi-core systems first became very popular. And one application, when you run these two applications together, one application slows down by very little, and the other application slows down by a lot, even though this may be the high-priority application that you really care about. And you cannot fix the problem in the operating system because these are always scheduled in the two cores. Those are the two applications that you're running. And this happened, if you remember, because we had these two different applications generating requests, and the memory controller was unfair. In this case, the memory controller is the culprit because caches were actually, initial multi-core systems, caches were not shared across these different cores. Okay, basically the streaming application, if you remember again, jogging your memory, would deny service to the more random access application because the memory controller was prioritizing the requests that hit in the row buffer. You remember this a little bit? Okay. So I also said that you could actually write this memory performance hog. This is a streaming application, which basically copies one array to another and also does other things to the arrays. But it does so in a streaming manner. It's sequential memory access. As a result, it's basically going through the row buffer. It has a very high row buffer hit rate for both of the arrays in two different banks. Of course, now you can think about, oh, if these actually go to the same bank, you have bank conflicts. That's probably not a good idea. But hopefully they go to different banks. And this is very memory intensive because we ensured that to be memory intensive. As you can see, every single access goes to a different cache line over here. Assuming you know the cache line size, you could actually ensure that that happens. This is the dual of this application. And it does exactly the same things, copies one array to another and does other things to the arrays, but does it in a random access way. Basically, if you see over here, the indexes are formed in a random manner, pseudo-random manner. As a result, you get very low row buffer locality because the index that you're accessing now doesn't have anything to do with the index that you're accessing in the next iteration, and then the next iteration, dot, dot, dot. So you get very low row buffer hit rate. And it's similarly memory intensive. And if you run these applications together, if you remember, this is what happens in an existing memory controller that optimizes for row buffer locality. Basically, it prioritizes the requests that go to the same row, and by nature, the requests of a streaming applications keep hitting in the row buffer. And as a result, the random access application doesn't get its service for a long time. This is the Tannin bar problem. Except it's not exactly the Tannin bar problem because Tannin bar doesn't have the row buffer, right? Tannin bar problem that I described was really a memory intensity problem. So even if you remove the row buffer, if you have memory intensity, let's say, and if you're doing first come, first served scheduling, and assume that the red application has very few requests, the blue application generates, let's say, 128 requests. They get queued in the buffer, and the red application generates one request. If you're doing first come, first served scheduling, the blue application's request will be prioritized naturally because it has lots of requests in the queue, right? So it's a similar problem. It may happen because of the row buffer. It may happen because of memory intensity. Okay. So current controllers actually take advantage of the row buffer, as we've discussed. They use the first ready, first come, first serve, or row hit first scheduling policy. They service row hit memory access first, and all else being equal, they service all their accesses first. So basically, if there are no row hits, or if everything is a row hit, then they do oldest first scheduling, which is first come, first serve. And both of these properties are actually unfair. Well, the property is actually, this is not a bad scheduling policy if you're running only one thing in the system, one thread in the system, because you're really trying to maximize the DRAM throughput or minimize the latencies, right, by making the most out of the row buffer. But if you have multiple threads that are sharing the DRAM system, you have unfairness. And these are the past works that actually propose this policy and other policies related to it. Okay, so the streaming application and the random application, these are real system results from 2006 or so. Basically, when you run these two applications, stream slows down by about 18%, and the random access application slows down by almost 3x, 2.8x, which is not good. And actually, it turns out the stream is a very good memory performance hog. If you run it with something like GCC, for example, GCC slows down a lot, stream slows down little, again. And if you run it with something that I'm not sure exists anymore, but this is Microsoft's virtual machine at that time. It's virtual PC. We just wanted to run it to show that you could actually deny service to virtual machines, which are supposed to provide some isolation, at least at the software level. It happens, again, basically stream denies service to this virtual PC, degrading its performance by a lot. Because this interference is happening at the very low level that the software is not able to control. Okay, so this becomes a greater problem with more cores. This is, again, another result. Basically, these are 4 different applications run together, and the slowdown each of them experiences compared to when it's run alone on the same system. As you can see, one application, this is very, very streaming, very memory intensive also. It slows down by only 5%. Another workload, this is a network simulator, that slows down by about almost 8x, 8 times compared to when it's run alone. And this is H.264. It's basically a video encoder that slows down by about 5x. So this may actually have quality of service guarantee requirements, right? So basically, you become not only vulnerable to denial of service, basically this is denying service to other, intentionally or unintentionally, but you are unable to enforce priorities and service level agreements because we're not really controlling this. And this also leads to low system performance. Why? Because now you have 4 different cores. One of them is making progress, maybe. It's not slowing down. But this other one is slowing down a lot. Well, this one actually is not making a lot of progress because it's the one that's actually very, very memory intensive. And it turns out this is not very memory intensive. So what's happening is the core that's making really slow progress is being prioritized, and the core that could otherwise make really fast progress is being denied service. So if you are looking from the system throughput perspective, you have these 4 different workloads that you're trying to run, and you're slowing down the thing that could utilize its cores really fast, a lot, and you're giving priority, or unfairly prioritizing, the workload that is running slow anyway. So that's really bad for system performance. Basically, if you actually prioritize the one, so let's assume this has 100 requests and this is only 1 request. If you actually prioritize this 1 request that Omnet PP has once in a while, you would reduce its slowdown a lot without significantly increasing the slowdown of this one, because this will have 100 requests anyway, and it'll have to wait anyway. So basically, we're doing the wrong thing by prioritizing the core that's making slow progress. So that leads to low system performance, overall system performance. So clearly, their interference causes a lot of other issues, as you can see over here. But basically, you have an uncontrollable and unpredictable system. How do you actually do what I said? Basically, figure out that Omnet PP once in a while generates requests and prioritize that request such that it can make fast progress in its course without degrading the performance of other applications by that much. You need some controllability. And you can read the papers for more detail. Basically, this happens in many, many systems. As long as you have resource sharing and resources are not shared in a controllable manner, you have this problem. Okay, so let me give you a bigger scope of the problem. As systems scale, this problem actually becomes worse. And this is one way of scaling a multi-core system today. Basically, I think it's a 64-core system. You have 64 different cores, and each slice over here may be a core and a shared cache slice, for example. And you may have memory controllers located at different points. So this may be a memory controller, for example. And this paper talks about an example system like this. But basically, you may inadvertently slow down many applications in the system if you have this sort of resource sharing. So in this case, you have actually routers that are connecting the different blocks over here. It's called an on-chip network, which we will cover. That's how you can scale the size of a multi-core system by building, let's say, an on-chip network that connects 1,000 cores. In this case, it's 64. And that enables you to have a very regular structure, at the same time having scalability, but it also causes resource contention now. For example, if all of these cores want to access this memory controller because their memory happens to be mapped over there, they may actually go through this path. They may send a lot of requests that go through these paths if you do the routing in some fashion. If you look over here, the routing is done at the X route first and then the Y route next. As a result, you get a lot of contention over here, and especially over here. And it turns out if you don't control this sort of interference, you get significant slowdowns. For example, this paper shows cases where your latency is increased by about 5,000x. As you scale the systems, basically numbers become higher and higher. So you really need to control this sort of interference and be intelligent about designing systems to minimize the interference. Okay, so these are some of the papers that I will mention. I'm not going to go over this, but when we talk about interconnects, actually, we're going to cover some of these issues. And again, this is not an on-chip problem, right? The same interconnect actually exists in a data center, internet. Also, if you've taken a networking course, you will have seen a lot of quality of service mechanisms. How many of you have taken a networking course? Okay, have you seen quality of service mechanisms in TCP? Yes? Okay, great. Yeah. They actually do, for example, congestion control, throttling, right? Which we will talk about also. If the packet latencies are increasing, if they're high or above a threshold, they actually throttle back. And they have things like exponential backoff, for example. If the packet latencies keep increasing, they keep backing off more. Okay, so similar things exist at the on-chip level as well. But of course, on-chip has different constraints, right? Cache, maybe a lot more complexity internally over here. And also, you need to make decisions very quickly on chip. But we'll talk about that when we get to the interconnects. Okay, basically, how do we solve the problem? So inter-thread interference is uncontrolled in all memory resources that we have today. The solution is we need to somehow control it. We need to, I'm not sure if there's any other solution to this other than paying a lot of costs and partitioning your resources across different threads, which has its own set of problems. Basically, we need to design an interference-aware or quality-of-service-aware memory system. So there are three major questions associated with this. And again, any resource that you design, you need to talk about these questions. First of all, you would like to reduce the interference that happens as much as possible, because if you can reduce the interference as much as possible, it's much better than managing it when it happens. So this improves system performance and core utilization, and this can reduce request serialization and core starvation. Well, how do you reduce interference? For example, you don't have 100 people batches that go into Tannin bar. You have one-person batches, maybe. That's one way of reducing interference. Of course, that may be very difficult to do because you don't control people, right? You don't control how many people come in batches. So this has issues also. But we will see some other cases over here in the context of memory controllers. The second is you need to control inter-thread interference. Even though you may not be able to reduce it, you can control it. Basically, provide mechanisms to enable system software to enforce some quality of service policies while providing high system performance. So if you care about this thread, it should be prioritizable. And the system software should be able to tell the memory controller, oh, I really care about this thread. Its latency should not be slowed down by this much, by more than this much, by more than 2x, let's say. Or it could convey priorities. This thread has a priority of 4. This thread has a priority of 2. Now, what does that mean? I don't know, but it's clear it means that this thread is more important than the other one, right? So that's one problem with priorities, actually. If you look at operating systems, usually priorities are very ad hoc, right? Have you ever messed with priorities in your operating system? Done nice, for example, in Linux? So in Linux, for example, you can set the priority of your own processes using nice. Nice means be nice to others. So you could actually reduce your priority or increase your priority. But the classic criticism of priorities is they don't have a very good or rigorous or formal way of affecting or providing quality of service requirements. So what does a priority of 20 mean versus a priority of 1? I don't know. High, low. I don't know. High means, high is definitely higher than low. Does that mean I should always prioritize the high one? Okay. So that goes into the core of quality of service. So actually, you really want, if you want to be really rigorous, you really want to say, this program should take this long. And I can tolerate maybe 99% of the time, I can tolerate this much latency increase. But if it's more than that, I cannot tolerate it. For example, another quality of service is when you're displaying something on the screen, you should display at 30 frames per second. Actually, people are pushing at 60 frames per second these days, right, with high-quality videos. So that's a clear quality of service requirement, 30 frames per second. Even that's not perfectly clear, right? Does that apply to 100% of the time? Does it apply to 80% of the time? 99% of the time. So that's the difficulty of quality of service in general, quantifying what you really want. And that's also the difficulty of service level agreements, which actually build on quality of service. Okay, but it's clear that there is at least some ordering if you have priorities. It's better than having nothing. So I know, for example, that my virus checker is not important compared to the email that I'm trying to write at this moment. Right. Okay, so we would like to control inter-thread interference. This is actually relatively easy. I'll give this example. So you may actually have 1,000 cores. If you really want to control the inter-thread interference, you run only one application or one core, and everything else stays idle. So fairness is easy if this is not a constraint. So if you really want fairness and high system performance, then this problem becomes interesting. And the third issue is you want to make the memory system configurable and flexible, because if you would like to control inter-thread interference, there's not always a single goal, right? Applications may have different goals. Different virtual machines may have different goals, different requirements, basically. Sometimes you don't really care about fairness or throughput. Or sometimes you don't really care about fairness. Throughput is all you want. Sometimes you really care about the performance of a single application, and you really don't care about the performance of the overall system, right? And sometimes it's in between. So you really want a configurable system that can understand these requirements. Okay, so there are two approaches in building such systems. I'll cover both. So the first approach is to design each of the shared resources to have an interference control or reduction mechanism, configurable one. So we have many shared resources, I said, memory controllers, interconnects, caches, ... and design each of them to be intelligent, if you will, or smart, such that it understands the interference and it tries to control it and reduce it. The second approach is to keep them dumb, or as dumb as possible. So clearly this one requires modifying all of the resources, right, and communicating the information to all of the resources, information of quality of service requirements. The second one, you keep each resource as it is today, or even today is actually, there are a lot of smart resources that we have. Today is not 2005, 2006. Today is 2017. So today we already have smart resources, but okay. Keep each resource free for all, so that you don't actually put a lot of effort into designing the resource itself. Like memory controllers are kind of dumb, let's say. They're first ready, first come, first serve, maybe with little tweaks. But you reduce and control interference by controlling something else in the system, by controlling the injection into the system, which memory requests get injected, which threads can inject, and by controlling the data mapping, such that things are isolated from each other as much as possible. So we'll cover this approach as well. And it turns out I'll give you the result. You really want both of them if you want quality of service. And people are still trying to figure out what is really best. So for example, from the network perspective, since some of you have taken network courses, you could think of this as routers. Router is a very precious resource in the network, right? Each router may have no quality of service mechanism, right? It basically takes all of the requests as they come, first come, first serve. Today's routers are not that way, but you could design it that way. That's a dumb resource. But the injection control into the network on the endpoints can be intelligent. You basically coordinate the injection somehow, again, I don't know how, such that things that require high quality of service get priority in the injection, and they can go through the network relatively quickly. It turns out to be not so easy to do that, because you really need to actually keep information in the network about what's making progress and what's not making progress, and propagate it back to the nodes that are injecting into the network, and then throttle the injections in a manner that's coordinated across many, many things. So this is really difficult to do in the internet, of course, right? Because how do you actually control some person from, I don't know, New Zealand's injection when you want your quality of service in Switzerland, right? But in an on-chip context, these things are imaginable, because you can actually coordinate different injections. Okay. And the other approach is, of course, making the routers very intelligent, such that they can understand the quality of service requirements of different flows, different applications, and they can actually do the scheduling internally, such that they provide the quality of service requirements to different flows. Of course, the downside of this one is how do you coordinate across those smart resources, right? You have many, many routers. They all need to coordinate with each other somehow. If one makes decision X and the other one makes a decision that goes against this decision, then you have a problem. Okay, so we're going to focus a lot on memory controllers today. But before that, I'll cover some fundamental interference control techniques. I've already said many of these, actually. So the goal is to reduce and control inter-thread memory interference. We're going to focus a lot on this one first, prioritization or request scheduling. But we'll also talk about data mapping to different banks, channels, and ranks, core and source throttling, and application and thread scheduling. Let's jump into the first one. Any questions so far? I feel like I've talked a lot. Hopefully it's intelligible. Good. Okay, so basically we're going to focus on this thing over here, which is the memory controller. And memory controller's job will be to resolve memory contention by scheduling requests. And we already know that it has many, many other jobs. We're going to add more to it. So the key question is, how do we schedule the request to provide high system performance, high fairness, and configurability to system software? I'm not going to tackle all of these at the same time for everything I discussed, but I'll give you some bits and pieces. So clearly, for this to happen, memory controller somehow needs to be aware of the threads that are running on the cores, or hardware context. So when I talk about a thread, it will really be a hardware context. It's not the software construct, but it's really this hardware entity that's currently running in the context, in the thread context of a core. And for now, for simplicity, let's assume that one thread runs one core. One core runs one thread. So we'll cover a lot of mechanisms. This is actually an abstract evolution that talks about what we're going to cover. I'm not going to talk about that at the moment, but you can go back and refer to it. And we're not going to cover all of this, sorry. But this is, it's always good to summarize everything with a single key idea and takeaway. We may get back to this later on. Okay, good. Now I've covered 40 slides. Just kidding. Okay, so let's talk about the first one. Basically, the first issue that when actually people first started looking at this, and when we first started looking at this, we realized that the slowdown is a problem, right? Clearly, you have this unfairness in slowdown. Wouldn't it be nice if we actually designed a memory system that was much more fair in terms of slowdowns? That was the idea. Since the problem is this disparity in slowdowns, why don't we have a memory scheduler that's fair in terms of its slowdowns? Basically, the goal is to ensure that threads that are sharing the main memory experience similar slowdowns compared to when they run alone. That's the definition of fair scheduling in this case, right? Everybody can always argue with the definition of fairness. That's one of the issues, as we've discussed, right? But this is one definition of fairness. And the reason why we wanted this, we wanted proportional slowdowns for different applications, because it takes into account the inherent performance of the application, actually. If you have a very fast application, you slow it down by 10%. And if you have a really slow application, you also slow it down by 10%, right? You really take into account the inherent performance. And also, hopefully, it makes proportional progress. Sorry, I'll continue for a while, and then we'll take a break. Basically, a lot of operating system mechanisms actually assume that when they schedule a job or an application onto a core, they assume that it makes progress. And they implicitly assume, even though they don't always do the scheduling in a formally nice way, they implicitly assume that the progress that each thread makes is proportional to each other. That's why this makes a little bit sense, at least, from that perspective. So, of course, if they do the scheduling assuming that each of the cores make some proportional progress, then it's probably a good idea to slow down all of those cores in a proportional way. So the idea is, once you have this definition, the idea is to have the memory controller estimate each thread's slowdown due to interference, i.e. compared to when it's run alone on the system, and schedule the request in a way to balance the slowdowns. That makes sense, right? So everybody gets 1.2 slowdown, 20% slowdown. Everybody gets 4x slowdown. Maybe that's not a good idea. Okay, so how do you actually do this? It turns out this is not easy to build, so I'm not going to recommend that anybody builds it. Maybe we'll talk about some methods to estimate this later on when we talk about predictable performance. But when we first started, we were naive, And this was actually what we decided to do. Basically, we defined a DRAM system to be fair if it equalizes the slowdown of equal priority threads. Again, equal priority is important here, because if you have a high priority thread, you want to treat that differently, relative to when each thread is run alone on the same system. So basically, DRAM-related stall time, what is that? It's the time a thread spends waiting for DRAM memory. And you have a DRAM-related stall time when the thread runs with other threads concurrently. Let's call that stall time shared. You also have an inherent DRAM-related stall time when you run that thread alone, without others in the system. And the memory slowdown is defined as stall time shared divided by stall time alone, which is really the relative increase in stall time due to interference, due to resource sharing. Now, the goal of the stall time fair memory scheduler is to equalize this memory slowdown value for each thread that are interfering without sacrificing performance. And as I said, it has these two properties that are nice, hopefully. Okay, so the key question is, how do you do that? Without, of course, falling down. Of course, it's not easy to design this controller, but basically for each thread, the memory controller needs to track stall time shared and estimate stall time alone. Tracking stall time shared is not that hard. If you read the paper, you actually figure that out. Basically, whenever a thread is stalled, you count that, right? That's basically how much time you're stalling waiting for DRAM. Not whenever it's stalled waiting for DRAM, of course. But you can actually count this. There exist performance counters that count this. They may not be exposed to the system. But this is easy. The difficult part is figuring out what is the stall time of the thread, or what's the performance of the thread when it's running alone. The thread is not running alone, right? The thread is actually running together with other threads. How do you figure this out? Well, one option is to say, I'm going to kick everyone else out, and I'm going to look at the performance of this thread. It turns out that's really terrible, actually, because that destroys the performance of the system. You might as well not do this. So you really want some mechanisms and hardware to estimate this. And I'm not going to talk about that, but basically, the key insight is whenever you have a thread A, let's say, has a request outstanding, and it cannot be serviced in the memory controller because a thread B is being serviced because of some contention, then you actually count some cycles, saying that, oh, these are the cycles that I'm waiting because there's some interference that's happening from some other thread. And you keep counting those cycles. Let's call those excess cycles or interference cycles. And if you count them nicely and well, which is really a hard problem, you can subtract those cycles from the stall time shared, saying, oh, these were the cycles that I stalled because of interference. If I subtract them, I will get stall time alone. Right. Theoretically, this is possible, and this paper shows that actually you can get close, but not perfect. So let's assume that you've estimated this. So clearly there are a lot of issues over here, right? Because what if you have many, many requests outstanding from a thread? You all have gone through the memory level parallelism lectures. We've discussed overlapping of latencies. If one request gets delayed, another request may not be delayed. So how do you take into account that overlap becomes really, really hard? So assuming that you can do it, and this paper does it somehow with a real mechanism, which is hard to implement. Each cycle, the memory controller estimates a slowdown, stall time shared divided by stall time alone, for threads that have legal requests, which means that you can actually schedule that request. And it computes some unfairness value, which is the maximum slowdown in the system divided by minimum slowdown. How unfair you are to all of the threads in the system. For all threads where you have a slowdown value, you find the max and you find the min and divide them. And if this unfairness is acceptable, and someone needs to provide this unfairness threshold, if it's below some acceptable unfairness threshold, then you use the regular scheduling policy that optimizes for DRAM throughput. Everything is good. If this unfairness is not acceptable at the moment, then you switch to a fairness-oriented scheduling policy and you try to reduce the unfairness. How do you reduce the unfairness? Well, it's probably a good idea to prioritize the request that has been slowed down the most at that point in time. And of course, you have a prioritization-based scheduling policy. Given this, maybe you still want to prioritize row hits from that thread, right, to maximize performance. So that's the key idea, basically. You figure out the unfairness in the system, and you keep switching between two policies. If unfairness is under control, that's good. You use the you do business as usual. If unfairness is not under control, then you switch to a policy that tries to ensure fairness. Let's look at this. Let's look at how this works in action with this picture. Basically, we have two threads again, thread 0 and thread 1. Now the memory controller needs to keep track of slowdowns as well as unfairness. And let's assume alpha, the acceptable unfairness threshold, is 1.05. This is very strict, of course. So, okay, initially, you have this request. Okay, you schedule it. Initially, unfairness is not a problem. It's less than alpha. So you keep using the throughput-oriented scheduling policy, which is row hit first. So you have these two requests. This is row hit. So you schedule thread 0's request. When you schedule thread 0's request, you caused interference to this request. So thread 1 slowed down a little bit. Right? So you keep track of that. Because this, if this thread was running alone, it would have been scheduled, and it wouldn't have had to wait for this request. As a result, it slows down and unfairness increases. But in the next scheduling cycle, unfairness is still under control. So we keep using the row hit-based scheduling policy. At that point, you slow down the thread again, and unfairness increases. Right? And when unfairness increases here in the next cycle, you switch to a fairness-oriented scheduling policy, which prioritizes the thread that has been slowed down the most, which is thread 1 in this case. And the memory controller schedules that. Now, when you schedule this thread's request, you caused interference to this request over here, which basically changed the row buffer clearly. And that increases the slowdown of thread 0. Right? Now, unfairness is back in control. Right? And then, basically, you go back to the throughput-oriented scheduling policy. In this case, first come, first serve, because there is no request that hits in the row buffer anymore. And that increases the slowdown of both threads. Why both threads? Well, because when you figure out that you try to access row 0, if you were running alone, you would have had row 0 over here, right? But somebody else interfered with you, and you have now row 16 over here. So you get slowed down, actually, with this request. Yes? Uh-huh. So that's right. That really depends on the alpha number in that case, basically. If you increase your alpha number, alpha value, actually, then you exploit more of the row buffer locality over here before switching to a fairness-oriented scheduling policy. Or you could actually add mechanisms to add more hysteresis. Right? But we'll get to better scheduling policies. This is just to give you an example. Okay, so basically, this hopefully gives you an example of why this is not so easy to do, because you really need to now keep track of the row buffer that would have been open if this thread was running alone, right? So that's one problem in figuring out the alone performance of a thread. So clearly, this slowdown increased, and this slowdown also increased because you've scheduled a request from the blue thread, or T0, and you delayed this request. But unfairness is still under control. And then you do the row buffer hit-based scheduling. That increases slowdown over here and increases unfairness. So basically, you keep going back and forth between the fairness-oriented and throughput-oriented scheduling policy, while exploiting some row buffer locality, as you can see. Right. Okay. Okay, I think I will stop here. Well, I will not stop here, not the lecture, but we will stop here at the end of this and take a break. But basically, it turns out this improves performance significantly, as we will see later on. But let's talk about the upsides and downsides very quickly before we take a break. So the upsides, it turns out this is the first algorithm for fair multi-core memory scheduling that's specialized for the memory system that we have in a multi-core. There were previous proposals that basically apply scheduling in a router to the memory controller, but that doesn't take into account the row buffer, for example. And they usually don't take into account the baseline performance of an application. And it provides a mechanism to estimate memory slowdown of a thread. If you can do this well, this is actually a really good thing to do. It turns out it's very hard to do. Because if you can estimate the memory slowdown of a thread, now you know how far away from you are from your performance goal. And it's good at providing fairness, and you can see the result. And being fair can improve performance. This actually improves performance compared to a first come, first serve as well as first ready, first come, first served scheduler. Now, the downside is it doesn't handle all types of interference, and you will see what I mean in a little bit. It's complex to implement, and slowdown estimations can be incorrect. Actually, they are incorrect, but it still works because even though you may not have the perfect slowdown estimation, you're still getting the higher order bits right, saying you're still able to figure out, oh, you're unfair at this point. Maybe your slowdown estimation is saying, oh, you're slowing down this thread 80%. In reality, you're really slowing it down by 150%. But it doesn't matter as long as you get the higher order bits right, saying, am I unfair or am I fair at this moment? Right. Okay, so if you can actually do the slowdown estimations correctly, you can do performance isolation potentially by trying to even control things such that when a thread actually exceeds a performance requirement or it slows down beyond the performance requirement, you prioritize it. But in this case, you cannot do it because the estimations are not accurate. But for the purpose that we need it, they're accurate enough. Okay, so this may be one of your readings in the future. But I think let's take a break here for about 7 minutes, and we'll continue our exploration of memory scheduling. Okay, let's get started. We're going to cover a lot of ideas in memory scheduling, so hopefully you're ready for this. Okay, so that was stall time fair memory scheduling. And then we became smarter. We figured out that things should not be as complex as stall time fair memory scheduling. And there are a lot of other issues, actually, in memory scheduling. So let's cover some of those issues. So one issue is actually very interesting. That happens mainly in processors. I haven't seen it anywhere else, actually, but it could happen somewhere else also. But if you look at processors, they try to tolerate the latency of DRAM requests by generating multiple outstanding requests. And we've seen this before, right? This is the concept of memory-level parallelism. Out-of-order execution, non-blocking caches, those misstatus handling registers that we've seen, run-it execution, which we will see later on. I briefly talked about it when I presented some data. They're all there to exploit memory-level parallelism, meaning generate many requests at the same time. Now, this is effective only if the DRAM controller actually services the multiple requests in parallel in the DRAM banks. Right? Well, there are two requirements. First of all, the requests should go to different DRAM banks such that they can be parallelized. That's kind of obvious, hopefully. If they go to the same bank, then you have serialization. But even if they go to different banks, DRAM controller should service them in parallel at the same time. But when multiple threads share the DRAM controller, this may not be the case because DRAM controllers are not aware of threads' memory-level parallelism. As a result, they can service each thread's outstanding request serially, not in parallel, even though they go to different banks. And I'll show this pictorially to you. Basically, this is really the destruction of bank-level parallelism of a thread. Now, let's look at the single-thread execution of a thread. Basically, you do some computation, and then let's say you stall for 2 DRAM requests, and these DRAM requests are sent to 2 different banks. Assume that they map to 2 different banks. The memory controller receives them and starts them in consecutive cycles. So most of the latencies of these 2 requests to 2 different banks are overlapped. And the thread stalls for approximately 1 bank access latency plus some change over here, right? So the bank access latencies of the 2 requests that this thread is waiting for are overlapped. So you stall for 1 bank access latency. Now let's take a look at a very simple case where we replicate this thread and we run 2 threads that do very similar things. Thread A and thread B compute, and they both reach 2 DRAM requests almost at the same time. These requests arrive at the memory controller, let's assume in this order. First arriving one is this one, last arriving one is this one. And the memory controllers somehow, and ignore the rows actually don't matter that much over here. We're just looking at banks over here. But let's say memory controller takes thread A request to bank 0 and schedules it. And then thread B's request to bank 1 and schedules it. And both threads wait until both the requests are being serviced. And then this request is done in the bank. The memory controller takes the next request to bank 0 and schedules it, which happens to be from thread B. And then this request is done in bank 1. And then the memory controller takes the next request to bank 1, which happens to be from thread A. And then both threads still keep stalling because they need to wait for the request to be serviced over here. And eventually, the requests are done, and the threads can make progress. Now, if you look at what happened, is the bank access latency of each thread became serialized. Even though they were perfectly to different banks, they got serialized because the memory controller serviced them in an order such that they were not overlapped. As a result, each thread stalls for approximately 2 bank access latencies. Now, the question is always, can you do better? And the answer is clearly yes. If you had a parallelism-aware scheduler, when it received these 4 requests in the same order as before, it could have been a little bit more intelligent. It, let's say, first took thread A's request to bank 0, and then next, instead of taking thread B's request, which is the next one in the queue, it would ask the question, does thread A have any other request to any other bank? And the answer is yes, so it would next schedule thread A's request to bank 1, such that it would overlap the latencies of thread A's 2 requests. And when one request is done, it would basically take the thread B's request to bank 0 and schedule it. And when the next request is done, it would take thread B's request to bank 1 and schedule it. But now thread A is done with its request. Now it can continue computation, right, in its course. Now thread B keeps stalling until its requests are done, but doesn't stall any more than it would have stalled over here. So we saved a lot of cycles on thread A by ensuring that its requests are serviced in parallel and the latencies of those requests are overlapped in the banks. So that's the idea. Basically, by making the memory scheduler aware of the memory level parallelism or bank level parallelism of a thread, you can achieve a much better scheduler. So average stall time that you have for threads right now is 1.5 bank access latencies as opposed to 2 over here. Okay, so that sounds good, right? So how do you make it work? So the first principle I've already shown you, basically. It's called parallelism awareness. The idea is to schedule requests from a thread that go to different banks back to back. So if you pick this thread to schedule, keep scheduling its requests back to back to different banks, such that you can maximize the bank level parallelism of that thread. Now, the problem with this is if you employ only this principle, this can cause starvation, because it might happen that the thread that you picked is a very aggressive thread. It has lots of requests. And when you actually schedule its requests, it quickly generates new requests from the core. As a result, it may actually deny service to other threads. So to eliminate starvation, the second principle is called request batching. This is actually a really old principle that's used in hard disks in 1960s, the first time. The basic idea is to group a fixed number of oldest requests from each thread into what is called a batch, and service that batch before all other requests. So all these requests that are in this batch are going to be serviced, and I'm not going to reorder any other newer requests into this batch, before this batch, and form a new batch when the current one is done. So this eliminates starvation and provides fairness, and allows parallelism awareness within a batch. Now let's take a look at how this works with a pictorial example. Let's say we have 2 banks and 4 different threads over here, and we have 2 requests from each thread. This is a nice example. The memory controller first forms a batch, and you can form a batch because you may have other requests that are waiting over here, so you already have a lot of queuing in the memory controller. And the memory controller basically takes thread 0's requests first and schedules them in the banks. So it preserves thread 0's parallelism. Now look, in the meantime, there are some other requests that are arriving in the queue. So the queue is larger than the batch. The buffers are larger than the batch, but they don't get included in the batch because you already formed the batch, saying, I'm not going to include anyone else because those things are maybe going to cause starvation. Okay, so then the memory controller takes thread 1's requests and schedules them in parallel. Then the memory controller takes thread 2's requests in the batch and schedules them, but it's not going to take thread 2's other requests. Then the memory controller takes thread 3's requests and schedules them. And once this is done, you form a new batch. Basically, you ensure that this batch is done, which gives you a very clear bound of non-starvation, and then move to the next batch. And within the batch, you exploit parallelism. Okay? That's the idea. So, of course, there are details, and we will go into those details a little bit more. So we have 2 components, request batching, which is a really general component. This is actually, as I said, it was employed in multi-program disks. So disks have the same problem, actually. Whenever you do disk scheduling, and if you have many programs, and if you want to actually provide some fairness to different threads, people actually do batching of requests. And you have within batch scheduling, which is parallelism-aware. Now let's take a look at how batching is done. It's very simple. Each memory request has a bit called marked associated with it. And to form a batch, the memory controller marks up to some number of oldest requests per bank for each thread. And there are other ways of forming this, but this is how we formed it. And marked requests constitute the batch. And you form a new batch when there are no marked requests left in the controller. And marked requests are prioritized over unmarked ones. So this is an easy decision for the memory controller to make. There are no reordering or requests across batches, no starvation, as a result, high fairness. The key question is, when you have batch requests, how do you prioritize a request within a batch? And that's where things get a little bit more complicated. First of all, you can use any existing DRAM scheduling policy. You could actually use first ready, first come, first serve, which is completely unfair, and batching provides some fairness on top of that. So batching by itself is useful for fairness. But we want to do better than first ready, first come, first serve within the batch. We want to actually exploit parallelism, as we've discussed, right? We want to also preserve intra-thread bank parallelism. So for this, we want to service each thread's request back-to-back, which may go against the robo for locality, actually, principle. So how do you actually schedule each thread's request back-to-back? The idea is to form a ranking of threads when the batch is formed. You basically rank the threads, and higher ranked threads are prioritized over lower ranked ones. And if you do this, you improve the likelihood that requests from a thread within a batch are serviced in parallel by different banks. Because different threads are prioritized in the same order across all banks. Right? Because you have this ranking, and in all banks you obey that ranking. Thread 0 is higher ranked than thread 1, is higher ranked than thread 2. And if thread 0 has a request to any of the banks, that gets prioritized over thread 1's requests, and that gets prioritized over thread 2's requests. So that's a very rigid ranking scheme. The key question, of course, is how do you rank the threads, right? One option could be at the beginning, at the formation of a batch, you form a random order across threads. It actually is not bad. It still preserves parallelism, but it doesn't preserve it as well as what I'm going to describe in a little bit. So let me give you an example. What's thread ranking? So this is bank 1, bank 0, and these are the requests, thread B and thread A over here. And this is a scheduling order, assuming you schedule this one first, and this one next, and this one first, and this one next. That's exactly the problem that I showed you earlier. This is the memory service timeline. Both threads wait for 2 requests. Now, if you rank thread A higher than thread B, in this case, it doesn't matter which one you rank higher, actually. This is what you do. In both banks, you obey the ranking. As a result, memory service timeline looks more regular, like this, and thread A waits much less, so you save cycles. So even random ranking might work, actually. But we want to do better. So ranking scheme actually affects both throughput and fairness. We want to maximize system throughput, such that all threads make progress, a lot of progress, and minimize the unfairness. And again, minimizing the unfairness is equalizing the slowdown of threads here. So to maximize system throughput, if you really want to do this, you really want to minimize the average stall time of the threads within the batch. If you think about this, if you minimize the stall time of the threads. If you want to minimize unfairness, it turns out that's actually similar. But basically, you want to service the threads with inherently low stall time early in the batch. Because if you delay a memory non-intensive thread, that results in high slowdown, right? For example, if a thread has 1 request, if a thread's stall time to begin with is 1, if another thread's stall time to begin with is 10, if you delay both of them by 1 time unit, this one slows down by 50%, or 100% actually, and this one slows down by 10%. Right? So if you want to be fair, you really want to prioritize the threads that have inherently low stall time, or threads that are actually not memory intensive, if you will. So it turns out the shortest stall time first, or shortest job first ranking provides approximately both goals. And the idea over here is actually estimate the stall time of the threads within a batch and figure out the shortest jobs and order them based on the shortness of the job. Like order the one with the stall time equal to 1 first, stall time equal to 3 next, stall time equal to 5 next, and that's how you rank them. And actually there's a lot of studies in scheduling theory that shows that if you do shortest job first, that's the optimal system throughput, assuming you have a single server queue that doesn't have something like a row buffer. So people have actually studied this for factories, for example, and they figured out that if you have jobs that are going to the same factory and they have different amounts of time in which they finish, if you want to maximize the job throughput or production in a factory, you really would like to do shortest job first scheduling. It really makes sense if you have a single server, single factory, doing only that thing at that time. Now we're going to borrow that concept, but it's not going to have the nice theoretical properties because memory system is complex. We don't have a single bank. We have many banks. And even within a bank, we have a row buffer. And if you want to actually analyze this theoretically, both of these properties make it really complicated. So if you look at scheduling theory, classical scheduling theory doesn't fully apply perfectly here. But we're still going to borrow some things. Okay, so basically that's the idea. But even then, it's not easy to figure out what's the shortest stall time first ranking. So basically, we're going to use some heuristics. The idea is to figure out, how do you figure out which thread has the shortest stall time within a batch? To be able to compute this, we want to find the maximum number of mark requests to any bank for each thread, max bank load, and we want to rank the thread with lower max bank load higher. And because this corresponds to low stall time, hopefully. Now, this is not perfect, as you can see, because if you want to really compute the stall time, you really want to do what we did in the previous stall time fair memory scheduling, right? If you want to look at a batch and you want to figure out the stall time of each thread, you really need to simulate the memory scheduling algorithm to be perfect. Because the stall time of a thread depends on what you've scheduled what you've scheduled in the past. And you don't want to do that. That's expensive. So we want to use heuristics. And of course, we also have the total number of mark requests to break the ties, because sometimes you'll have ties with this maximum number of mark requests. Now, let me actually motivate this a little bit, because this may not be easy to understand over here. So let's take a look at this more complicated example. Again, I don't have the row buffers here, because row buffers actually complicate things, but you can look at the paper. In fact, this paper will be assigned probably. You can look at the paper for the row buffer example. Assume nothing is row buffer hits over here. So let's take a look at these two properties of a thread. Max bank load. Let's compute it for thread 0. Thread 0 has one request, maximum of one request to any bank, so its max bank load is 1, and it has a total load of 3 requests inside the batch. For thread 1, its max bank load is 2. The maximum load it has on any bank is 2 requests, and it has a total of 4 requests. For thread 2, its max bank load is also 2. To these 2 banks, it has 2 requests each, and its total load is 6. And thread 3 is the heaviest. Its max bank load is 5 over here for bank 3, and it has a total load of 9. Now, this hopefully gives us an indication of the stall time, inherent stall time of each thread, because this is the longest delay that this thread is going to experience, assuming all of its requests are going to be serviced in parallel in the banks, assuming it's the only thread in the system. Right? So that gives us an indication of the stall time, inherent stall time, and that gives us an indication of the memory intensity and interference that's happening with other threads. Okay, so based on this, we're going to rank thread 0 higher than thread 1, higher than thread 2, because we have this tiebreaker over here. Hopefully thread 1 can be faster to finish because it has fewer requests, and thread 2 is going to be ranked higher than thread 3. Now let's take a look at an example within batch scheduling order. So I'm not going to fall down in this lecture, hopefully. Okay, basically this is the baseline scheduling order. I'm going to assume first come, first serve, because there's no row buffer over here. If you look at the baseline, and let's assume again abstract time, ignore all of the bus overheads, ... It's really bank access latencies. This is the baseline scheduling order. Basically, how long does thread 0 stall for these requests within the batch? Thread 0's last request gets serviced after 4th time unit, so it stalls for 4 bank access latencies. Thread 1's last request also gets serviced after the 4th time unit, so it stalls for 4 bank access latencies as well. Thread 2's last request gets serviced after 5 bank access latencies, and thread 3's last request gets serviced after 7 bank access latencies. So stall times are relatively high. And we could do better, and the average, of course, is 5 bank access latencies over here. So if you use parallelism-aware batch scheduling, this within batch scheduling order will be determined by the ranking that we have computed just now in the previous slide. So we're going to rank, prioritize thread 0's request over others, which means that thread 0's request will be serviced first in all banks. And as a result, it will have a nice stall time of 1. Thread 1's request will be serviced, prioritized next, and as a result, it will be serviced this way. Because bank 0 doesn't have any request from thread 0, it can service requests from thread 1, as you can see, right? Because it's a priority order. This ranking is a priority order. It doesn't delay requests from threads. As a result, the last request of thread 1 is serviced after 2 bank access latencies. So we're already having much higher improvements for these threads. Thread 2 is ranked the third. As a result, its last request gets serviced after 4 bank access latencies. And then thread 3 gets ranked that way. But if you look at this picture, we preserve the parallelism of many, many threads, as you can see, right, by enforcing this ranking across the banks. And if you look over here, the average bank access latency is 3.5 with this scheduling order. So we've improved performance by about 30% within this batch. Of course, there's the across batch component, which we're not showing over here. Okay. So what's the schedule? Yes?
How do we know the full scheme of the bank request? I mean, it can be changed dynamically.
Yes, so that's why we formed a batch to begin with. You basically do this within a batch. So only for the marked requests you form this ranking, and everything else that may be arriving over here in the request buffer, they're not going to be. They may be scheduled if there's a free bank. So that batch is prioritized over everything else. Yes.
Do you know what's the typical batch time?
Yeah, so you can read the paper for more detail. Basically, it really depends on how much load you have, how many cores you have. But the queue size in a lot of existing controllers could be 128, for example, 128 requests.
And do you know what's the overhead for rescheduling the requests within the batch to fit this scheme?
Say it again?
And do you know what's the overhead?
So you should read the paper. we'll talk about that very briefly. Yes. So there's no overhead in rescheduling, but there's hardware overhead. Right? There's no time overhead because you can overlap the latencies. Okay, so this is the scheduling policy. Basically, you prioritize a marked request first. That's really batching. It's really a prioritization order in the end, right? And this is always debatable, actually. Do you actually prioritize row hit request first or higher ranked thread first? This is within batch scheduling. It turns out there's always a tension between this parallelism awareness versus row buffer locality. And there's no perfect way of getting it. So if you read the paper, you will see that if you order this higher than the second one, you get very little performance degradation. Both are similar. But basically, you need to preserve parallelism somehow within the batch. So there are 3 properties of this. You exploit row buffer locality, as well as intra-thread bank parallelism with this ranking, as we've discussed. Unfortunately, you don't get the best of both worlds. Because these actually contradict each other. It's work conserving, meaning it's a prioritization order. It doesn't delay any requests. So you don't delay requests to form the batch. You just form the batch with requests that you see in the memory controller. If you delay them, that may or may not be a good idea. You can also service unmarked requests to banks without marked requests, meaning if a bank doesn't have any requests that are within the batch, it can service an unmarked request. And it turns out this is really important, the batch size, basically. If you're too small, you destroy the row buffer locality because you get fewer requests from a thread that may go to the same row buffer. And if you're too large, now you exploit high row buffer locality, but if your batch is too large, what may happen is you service a thread within the batch, and then it generates another request. Now that request needs to wait for the batch to complete to get access. So you penalize really memory non-intensive threads that generate fewer requests such that they may not be able to exploit the batch itself. Okay, there are many more trade-offs, but they're in the paper. So to answer part of your question, this is the hardware storage cost. So this is much cheaper than the stall time fair memory scheduler. So it's very little storage cost. There are no complex operations like divisions because you need a division actually in stall time fair memory scheduler to compute on fairness. And this is not on the critical path. Scheduler makes a decision only every DRAM cycle. But it turns out this is also complex, so we're going to go back to some other schedulers later on. So let's take a look at the performance and unfairness of this scheduler a little bit. And you will see this in the paper also, but this is unfairness, maximum memory slowdown of a thread divided by minimum memory slowdown. And these are different types of systems averaged across some number of workloads that you can find in the paper. As you can see over here, first ready, first come, first serve is quite unfair, right? This average across many workloads, your unfairness actually keeps increasing if you increase the number of cores. First come, first serve is better, but it's also unfairness also keeps increasing a lot. And this is actually, if you apply networking principles, do basically network fair queuing, which I'm not going to talk about, but you can read in the paper again, in the memory controller. It's not bad, but it's not better than first come, first serve, as you can see in some cases, in terms of unfairness. This is stall time fair memory scheduling, which actually gets unfairness to a lower point, but it's still increasing a lot as you increase the number of cores. And this is parallelism-aware batch scheduling. So it basically reduces unfairness significantly compared to stall time fair memory scheduling. Okay, and this is performance. So why does performance improve? Performance improves actually for two reasons. One is because you can exploit the memory level parallelism of each thread. So we've seen your average stall time reduces. But also there's another reason. Because you're more fair right now, your cores are better utilized. Some cores are not waiting there, twiddling their thumbs because of unfairness. They're actually making progress. And as a result, you get system performance improvements. And these look low, perhaps, but they're on top of the best previous policy, which is stall time fair memory scheduler over here. And if you look over here, this is first ready, first come, first serve, row hit first. On top of that, it's about 30%. Well, I guess it depends on the system. And the reason you don't get a lot over here is that now your system becomes more bandwidth bound. So your scheduling becomes has a less of an effect, less of an improvement in terms of performance. Okay, scheduling is important when you can play with something, right, in the system, meaning you're not completely bandwidth bottlenecked. Even when you're bandwidth bottlenecked, you can actually reorder things when you're multi-programmed. And also, you have actually some requests in the system, right? Okay, any questions? So I'm going to assign this paper, so you're going to have fun with it, hopefully. But let's take a look at the upsides and downsides, which will help you also. So this is actually the first scheduler to address bank parallelism destruction across multiple threads. So basically, we build these cores to actually generate memory level parallelism. It doesn't make sense for the memory controller to destroy that parallelism that the core is built to actually exploit. It's a simple mechanism compared to stall time fair memory scheduling, but we'll look at more simpler mechanisms later on. And batching provides fairness and non-starvation, and ranking enables parallelism awareness. The downsides, it doesn't always prioritize the latency-sensitive applications. It actually has this problem with latency-sensitive applications. So when you actually, meaning they may not be memory-intensive applications, right? So as I said, this batching actually inherently penalizes not so memory-intensive applications because you're batching, you're not really taking into account this core that's generating a request, and that's the only request that's outside the batch. Right? If you actually serviced it, you would break the principle of batching, but you would make this core make faster progress. And actually, the paper explores policies that try to break the batch, but it doesn't do a good job because that actually leads to the breaking of the non-starvation guarantees. Right? Okay, so this is one. There's also, of course, it's never simple enough, right? There's another downside that should be added over there. It's never simple enough. This actually adds some complexity. So if you're actually a memory controller designer, you need to think about how to design it such that you don't delay requests. You compute the ranking at the right time. But the good thing is you don't need to compute the ranking perfectly. If your ranking is good enough, or while you're computing the ranking, you don't need to stop the scheduling. As a result, you can actually compute the ranking, overlap the computation of the ranking with scheduling. Okay. So let's look at the next one. So after this, we tried to solve this problem, latency sensitivity. And the idea was to actually build a scheduler that provides very high system throughput. I'm going to give you a very quick summary. There's a lot of theory, actually, scheduling theory that we exploit in this paper, but I'm not going to talk about that in much detail. The goal was to maximize system performance. We didn't want to be fair. We wanted to explore the direction of performance as much as possible. And it turns out if you want to do that, you want to prioritize the thread that has attained the least service from the memory controllers. This is called adaptive per thread least attained service scheduling. That's hence the name Atlas. And the idea is we're still going to use ranking because ranking has all the benefits that we've described. But you rank the threads based on the attained service in the past time intervals. So if in the past the thread has attained a lot of service, it indicates that that thread is actually very heavy and you would like to deprioritize it. Because if you want to improve system performance, you would like to prioritize the threads that are actually running fast in their course. Right? Because if a thread has very few requests, if you service them very quickly, it will go back to its core and keep executing. Right? Whereas a thread has a lot of requests, 1,000 requests, let's say, and it needs to wait for 1,000 requests to make significant progress, even if you prioritize it, that thread is going to wait for 1,000 requests, right? So the idea of least attained service is keep track of the attained service of each thread in the memory controller. Let's say how many requests that you scheduled. In this case, it's really in terms of cycles. How many cycles have you spent servicing this particular thread's request? If that number is low, prioritize the thread in the next interval. So basically rank the threads based on that. And there's, of course, more that goes into it, but you can read the paper. And enforce the thread ranking in the memory scheduler during the current interval. So why does it work? It basically prioritizes these light or memory non-intensive threads that are more likely to keep their cores busy. And it actually does improve performance. This is actually system throughput. In a 24-core system, we always want to be scalable. And this is the number of memory controllers. And you get higher system throughput regardless of the number of memory controllers. As you can see over here, you have a lot of memory controllers, a lot of memory bandwidth, so scheduling matters less over here. Even then, Atlas provides you about 4% performance improvement. And this is actually a really constrained, bandwidth-constrained system. You have 24 cores and a single memory controller. As you can see, system throughput actually is low because of that. But you get much higher performance benefit compared to the best previous scheduler over here. And 24 cores, 4 controllers is probably a more reasonable configuration that's adopted by the paper. Okay, I'm not going to cover this in a lot of detail, but there's a lot of theory that goes into the design of the Atlas scheduler. Yes?
It's like if you look at the PRVS and STVN for one core, so basically PRVS is actually underperforming.
Yeah, over here. So, yeah, it can happen. Basically, this is a difficult problem.
Okay, maybe it's for 24-core system and the earlier system that you simulated for another number of cores.
Yeah.
Yeah,
the issue is there are knobs for each scheduler that you need to optimize for a given system. And if they're not optimized, you may not get the best performance. And in this case, they're not fully optimized for all of the controllers, basically, schedulers. But you have a good point, basically. You cannot take one configuration and then run it in some other configuration. So you really need to optimize your memory controller for the system that you're designing. None of these may be the optimal controllers, actually, over here, because it's a tough problem to find the exact knobs. Okay, so system throughput in terms of a 4-memory controller system, as we increase the number of cores, it turns out Atlas performs better as well. So the performance benefit increases as you increase the number of cores. And there's more detail in the paper, but I'm not going to go into detail a lot. But I'll give you the upsides and downsides. So the upside is, this is actually perhaps one of the best schedulers at improving overall system throughput because it prioritizes these compute-intensive threads. So if you want to optimize overall system throughput, you want to prioritize the compute-intensive threads. They have one request once in a while, prioritize it such that that thread keeps its core busy. And it's low complexity, actually. We didn't talk about this much, but this is one of the lowest complexity schedulers so far we've talked about, other than FCFS, FR-FCFS. You need to keep track of only one counter, which is how much service you've given to this thread. And that's what really determines your ranking. So the real complexity comes from ranking itself, which we're going to talk about also. And there's also coordination among memory controllers that happens infrequently. We didn't talk about this also, but if you think about parallelism-aware batch scheduling, the issue of memory-level parallelism doesn't happen only in one controller, right? What if you have 4 memory controllers in a system, and a thread sends requests to all 4? Now you want to actually coordinate those memory controllers such that they all have the same ranking, if you will, to be able to exploit the memory-level parallelism of a thread in the best way. Now that coordination not only adds additional complexity, it also raises the question, how often should you do this coordination? Right? Because if one memory controller is prioritizing thread 1 and delaying thread 2, if another memory controller is prioritizing thread 2 and delaying thread 1, you have the exact same problem we've started with. So you do need to coordinate the memory controllers. That's one issue with PAR-BS, and Atlas actually solves that problem nicely. And if you read the paper, you'll actually figure out what that problem is. So the downside of something like Atlas is really it treats these compute-intensive, low memory intensity threads well. The really high memory intensity threads, they're already slow to begin with. So if they're delayed too much, maybe it's not that bad. But it's really the medium-ranked threads get delayed significantly. Sometimes the lowest-ranked threads also. So it leads to very high unfairness in the end. So this is good if you want to optimize job throughput, but this is not so good if you actually want to optimize for fairness. Okay, so you can read that. Any questions? By the way, least attained service scheduling has been used in many, many other fields. For example, job scheduling and operating system scheduler. People found out that the reason is if the sizes of your jobs have a particular distribution, namely a Pareto distribution, it turns out ordering them in such a way such that you keep track of the length of the jobs, like shortest jobs, the length of the jobs, and ordering them in a shortest job first manner provides the highest system throughput. This is similar to the factory example that I gave you earlier. Now, if the length of the jobs have a particular distribution, it turns out you can estimate the remaining length of a job by keeping track of the current length of a job. So the Pareto distribution has this nice property called decreasing hazard rate. For example, if a job has run for a short amount of time, okay, let me actually put that back. If you have a Pareto distribution of the runtime length of the job, if the job has run for a long amount of time, you can tell that it's going to run for a long amount of time. Basically, based on how long a job has run, you can actually estimate how long it's going to run because of the distribution. Let me give you an example. The file sizes, for example, that are transferred over the internet. People have shown that these file sizes have a Pareto distribution, meaning it's a very long-tailed distribution. There are many, many small files, but the tail is large, meaning there are very few large files that occupy most of the sizes, overall size. Which means that by keeping track of how much of a file you've transferred so far, you can guess how much you're going to transfer more. So if you've transferred very little so far, you can guess, oh, this file is going to end quickly, because most of the files are very small. But if you've already transferred a lot, you can comfortably guess that you're going to transfer a whole lot more, because there are very few files that are at the end of that distribution. So people have exploited this to actually predict the length of how long you're going to transfer if you're transferred by this amount. And that's essentially the attained service that you have, how much you've attained service from the network while transferring this file. If you've attained a lot of service, you're going to need a lot more service in the future. And if you want to optimize for performance, prioritize the things that have not attained a lot of service because they're likely to be the smaller things. Essentially, yes. If you read the paper, actually, it's really trying to get the shortest job first. But the question is, without running the job in full, you don't know how short it's going to be. In this case, the job is actually a memory episode, if you look at the paper. But I'm not going to talk about that in detail. Okay, so let's move on to the next scheduler. Basically, we're trying to do better and better. And I've shown you some schedulers so far. Let's take a look at the performance and fairness of these schedulers. So this is performance over here in terms of weighted speed up, which you are hopefully reading in the papers what that is. We may or may not talk about that later on. But this is one metric for performance in multi-programmed workloads. Higher is better. And this is another metric for fairness. Lower is better in this case. And in this case, I actually changed the fairness metric because this is actually a nicer metric for various reasons. The fairness metric is not max divided by min anymore. It's really max slowdown. You want to minimize the maximum slowdown as much as possible, which is not a bad metric. Maybe it's not, again, fairness metrics are always debatable, but at least it bounds the worst case slowdown of any workload in this case. If that's what you want, that's not a bad metric. But if you actually use other metrics, this chart looks very similar. So with a number of workloads, this is what you get. Ideally, you would like to be here, right? Higher system throughput, lowest possible fairness. And lowest possible fairness you can get with this metric is 1 on fairness. So Atlas, as I said, is very good for system throughput. ParBS actually is good for fairness. It's not bad for system throughput. And stall time fair memory scheduling is not in the Pareto frontier, if you will. And first come, first serve is pretty bad, as you can see in both system throughput and fairness. And first come, first serve is actually pretty bad over here. So basically, none of the schedulers is good at achieving this ideal, basically. Okay, you don't provide the best fairness and system throughput. So you always want to provide the best and want to be configurable on top of that. So how do these work? So if you think about the throughput biased approach, conceptually, you really want to prioritize the less memory-intensive threads. If you look at memory intensity this way, the bigger threads are more memory-intensive. You really want to prioritize the smaller threads. You can think of these as mice and elephants. If you really want to maximize the speed, you want to prioritize the mice. They move fast. Elephants are slow, right? These are mice. If you want to, that's good for throughput, but elephants might die, right? Basically, they may starve if you actually prioritize a lot of mice before them. So that's really unfair to the elephants. On the other hand, the fairness-biased approach is more fair, basically. You take turns accessing memory. This is one definition of fairness again, right? For example, you basically prioritize this thread for a while, and then this thread for a while, and then this thread for a while, ... Now, it's fair for the elephants because it doesn't starve, but the mice are actually hindered now. People who are moving fast, or mice who are moving fast, cannot move fast anymore. So if you use a single policy, it's insufficient for all threads, as you can see over here. And that's the key realization of this work. You really need a heterogeneous policy. Whenever you're trying to optimize for multiple metrics, that should be obvious. And the key question is, how do you actually get that policy? So these mice, memory non-intensive threads, we want to prioritize them for throughput. That's part of the policy. If you want to be fair, the real unfairness problems are caused by not these really little mice, but it's really caused by these big elephants fighting with each other. So if you have these big threads, if you prioritize one over the other for a really long time, if you rank one over the other for a really long time, you're really causing a lot of unfairness over here. And they may not be exactly the same. Some thread may be in the middle between mice and elephant, right? Maybe a human. I don't know. That size, basically. If you prioritize that human over the elephant for a long time, you cause unfairness. So the key idea over here is, once in a while, shuffle this thread ranking in an intelligent way, such that none of these elephants or humans destroy each other's performance, right? Heavy threads. And it turns out memory-intensive threads over here have different vulnerability to interference. My vulnerability to interference is different from an elephant's, for example. Elephant is very intensive. So take into account that vulnerability to interference in terms of shuffling. So that's the idea. So this takes care of the fairness, and this hopefully improves performance. And this shuffling actually improves performance a little bit also, but I'm not going to talk about that in detail. So how does this work? Basically, the key idea is to group threads into two clusters, memory non-intensive and memory intensive. We could think of this as latency sensitive and bandwidth sensitive, and the paper actually uses those terms a little bit. And you prioritize the non-intensive cluster over the intensive cluster, but you use different policies, memory scheduling policies for each cluster. Within this cluster, you give higher priority to even smaller threads, rank order, and within this cluster, you actually use a shuffling-based ranking. Okay, let's go into this a little bit more. So how do you cluster the threads? This actually, as we go through this, you will see that it becomes complex, and also it becomes prone to issues. One issue is clustering. If you don't cluster well, you can immediately affect fairness and performance. So one way of clustering is mentioned in the paper. You basically sort threads by misses per kilo instruction, how many misses it generates per instruction. That's a measure of intensity of the thread, and the higher one is over here. And then you basically say the threads that consume a fraction of the memory bandwidth in the sorted order are non-intensive threads. That's one way of doing it. There are many possible ways of doing it. You could actually use machine learning algorithms, but you don't want to build that into the memory controller, perhaps, right? Okay. So there are thresholds. So once you start adding thresholds, things become more complicated. Okay. So between clusters, you prioritize non-intensive clusters. So that's a very easy prioritization, as you can see. It's 1 bit, basically, per thread. Why? Because non-intensive threads have greater potential for making progress, and also doing so doesn't degrade fairness if you've done your clustering right. If truly non-intensive threads are really here, they're light, so you will prioritize them for a short time, and they will get out of the way quickly, because they're not going to generate a request for a while. So hopefully it doesn't degrade fairness, because they rarely interfere with intensive threads. So what do you do in the non-intensive cluster? Basically, you prioritize the threads according to their intensity, the lower one being ranked higher than the higher one. And this increases system throughput for the same reasons that we've discussed earlier. Least intensive threads have the greatest potential to make progress in the processor. Same principle as Atlas, right? Now, the difficult part is really how do you handle this intensive threads, the elephants and humans, basically, not the mice. The idea is to periodically shuffle the priority or ranking of the threads. And this is good if all threads have the same behavior, right? But if threads are different from each other, then equal turns doesn't lead to the same slowdown, actually. So you need to be careful. So let's take a look at 2 threads. Let's have 2 intensive threads that are contending. And we're going to use random access and streaming again to see the very opposite sides. It's always good to look at these opposite sides and extreme cases to understand the behavior of systems. Which ones slow down more easily? Any guesses? Who says the random access thread is slowed down more easily? No grades, don't worry. Who says the streaming thread is slowed down more easily? Who says, I don't know? Okay, some people, that's good to admit that also. You can think about that a little bit.
Both have the same intensity or different intensity?
Assume they're the same intensity. That's a good point, yeah. You don't have enough information. They're the same intensity, yeah.
But it also depends upon the scheduler that you're using. Like if...
That's true, yes, that's true.
Because if there is a random access, so basically if you're using FCFS and like FR-FCFS and streaming is higher over for locality, so maybe the random access is thing. It also depends upon the scheduler.
So maybe the random access slow down more easily, yes. So you have the right answer, actually. I'm assuming the FR-FCFS scheduler, baseline scheduler, yes. So yes, the idea is correct, actually. This is actually from real system results, basically. This is a random access thread, and this is a streaming thread. If you prioritize the random access, this is what you get. Well, this is actually simulation, sorry. But basically, you get 7x slowdown on the streaming thread. If you prioritize a streaming thread, it turns out you get much higher slowdown on the random access. Well, why? I'll show you in an example. Basically, a random access thread is easier to slow down because it's more vulnerable to interference. And the reason is it spreads its requests across banks. And if you have a streaming thread that hogs a bank, this random access thread cannot make progress much. And the probability of something interfering with a random access thread is much higher because it really spreads all of these requests across these different banks. So let's take a look. So these are rows and banks that you've been used to it. Random access thread spreads its requests across banks. So it has high memory level parallelism. When it's running alone, it's nice, right? Okay. So that's the characteristic. All requests are parallel, high bankroll parallelism. Streaming thread does this basically. All requests are same to the same row. It has high row for locality. It may be streaming many, many more times, of course. So let's take a look at a scheduler where the streaming thread is prioritized or a random access thread. This is what happens. Basically, the random access thread needs to wait for a long time for the streaming thread's request to finish in this bank. And it gets stuck, basically, over there. Okay, so this is more vulnerable to interference. So this is one example characteristic that makes programs more vulnerable to interference, this random access characteristic. So if you're running together with a streaming thread, too bad, you're more likely to be vulnerable. So that's the idea. We're going to quantify the difference between the threads. And I'm not going to go into the detail again here, but we're going to have niceness, inspired by the niceness of Unix or Linux. Some threads have high niceness, some threads have low niceness. And bank-level parallelism provides you high niceness, but now you're vulnerable to interference. And if you're not so nice, you cause interference and you're less vulnerable. And there's a way of adding these up, heuristically again, that gives you a niceness metric. Let's assume that you have a good niceness metric. The idea is to basically shuffle these rankings such that the nice threads that are vulnerable to interference get more slots to be of higher rank. Unfortunately, I don't have the slides. I forgot to copy them, but when you read the paper, you'll find out. But basically, the probability of a thread that is nicer to become a higher ranked thread is higher when you shuffle the threads. That's the idea. You don't, the top thread is not equally the same thread. The nicer threads have more of an opportunity to be the top ranked thread, basically. That's the idea. Okay, any questions? Now, clearly, we've complicated the schedule a lot more now, right? And that's one of the downsides of all of this, actually. So how does this operate? It's actually similar to Atlas. During a quantum, you monitor the thread behavior, all the stuff. And beginning of the quantum, you perform clustering using memory intensity, and you compute the niceness of the intensive threads that are in the cluster, in the intensive cluster. And in the next quantum, what you do is basically you use the scheduling policy that we described, but at very short intervals, you shuffle the thread ranking. So you don't keep the same thread ranking over here in the intensive cluster, but you shuffle it. And shuffle it in the way that takes into account niceness. So this is a scheduling algorithm. The highest ranked threads are prioritized. Non-intensive. This means that non-intensive cluster is always prioritized over the intensive cluster. And within the non-intensive cluster, lower intensive threads are higher ranked. And within the intensive cluster, we do use rank shuffling. And after this, the next bit that we look at is row buffer hit, and the next bit that we look at is age, or older requests. And you can read the paper for details on the storage. So storage cost is higher than Atlas. Hopefully no computations on the critical path, but there's complexity associated with it. Okay, we've covered this, so I'm not going to go through this, but you can look at the slide. So where does this take us in terms of performance? These were the previous schedulers. It turns out TCM actually can break this Pareto frontier, and it becomes on this Pareto curve now. So none of these schedulers are better. Again, this is very workload dependent. So you may actually, all of this is actually very workload dependent, plus it's dependent on the knobs that you use for different schedulers. And different schedulers have different knobs. For example, this has a marking cap knob. This is a quantum size knob, and also that's one of the knobs over here. And this is an unfairness knob, as you, if you remember. I guess this doesn't have a knob. But I don't show the one that has the knob, actually. So for first ready, first come, first serve, if you remember, there's one knob you could have. You could have a limit on how much reordering you can do, right? So you could limit the damage of the row buffer locality. You could say, actually, this was used in one of the AMD's memory controllers. Basically, what they said was, you're not going to, whenever you see an open row buffer, you're going to only prioritize a limited number of requests that hit in the row buffer that are younger than the oldest requests in the system. And that's called FR-FCFS plus cap, which is not shown here. I think hopefully it's in the next slide. And that scheduler is better than FR-FCFS actually in many cases because it limits the unfairness, but it reduces the raw buffer locality exploitation also. Okay, but the key takeaway over here is by designing a heterogeneous scheduling policy, you can provide the best fairness and system throughput. So there's also a fairness and throughput trade-off that's exposed here. Different schedulers have different configuration parameters or knobs, as I said. STFM has this knob. First ready, first come, first serve has this knob, which is the cap, how much you allow reordering. So it has this weird curve, as you can see, with different values assigned to different knobs. PowerBS has the marking cap knob, so it gives you different points if you use actually different knobs for the scheduler. Atlas has the quantum length knob, and TCM has a much nicer knob, which is really this clustering threshold. Basically, which ones do you deem as the memory-intensive threads and which ones do you deem as the memory-non-intensive threads? And it turns out if you actually adjust this cluster threshold within reasonable bounds, you have a nice trade-off between fairness and system throughput. So all of these are actually acceptable schedulers, assuming, depending on your goals, and better schedulers than any of those. Okay, so it's a relatively robust trade-off. Of course, again, this is really dependent on the workload. Okay, so it's a tunable knob. Now OS can trade off between fairness and throughput. And we have not talked about that as much, but you could enforce thread weights, and all of the schedules that we've discussed in the past have this property. The OS can assign weights to the threads, and the memory scheduler can enforce thread weights within each cluster by changing the ranking based on the weights that are assigned by the OS. And exactly how you do it, you should really read the papers. Okay, I think I already discussed this over here. So let's talk about the upsides and downsides, and we're going to take a break. Like everything else, this is upsides and downsides. Upsides, at least for these workloads, it provides high fairness and high performance, but optimization is not easy. It caters to the needs for different types of threads, which was not present in any of the previous schedulers. Now, you can have a latency-sensitive cluster and a bandwidth-sensitive cluster. Right? And we're going to actually take advantage of this more and more, because you could actually form these clusters in different ways. For example, if you know the information from the software itself, you could bucket an application into a latency-sensitive cluster, right? And then prioritize that cluster over a bandwidth-sensitive one. Okay, and it's relatively simple, again, but relatively. So there are a bunch of downsides. How do you scale this to large buffer size? It turns out it's not easy. How do you optimize the knobs? That's not easy. And robustness is a problem, actually, in terms of clustering and shuffling. There's a lot of knobs or moving parts in thread cluster memory scheduling. If you get the clustering wrong, then you may actually destroy a thread's performance significantly in this case. Because if a thread is neither a mice nor an elephant, where does it belong, right? So there's been a lot of thought into putting more clusters, but that actually increases the complexity of the scheduler also. Okay, and ranking is still too complex. Maybe ranking is not the thing that you always want. And we're going to talk about that next, actually. Can we actually achieve at least a good amount of the benefits of the ranking while improving the performance and fairness even more? Any questions? Okay, we should definitely take a break now, because we're going to switch gears a little bit. How about an 8-minute break now? Okay, let's get started. Okay, remember this downsides over here. We're going to try to solve some of these. And this matters in different ways in different systems. For example, the scalability is a big issue if you have a CPU and GPU running together and trying to, when you're trying to actually optimize for both. So conceptually, actually, TCM is a very good fit for a CPU plus GPU system, because CPU applications tend to be latency sensitive and GPU applications tend to be bandwidth sensitive. But when you actually try to implement it in practice, the buffer sizes, the scalability is not very good. And we're going to talk about that briefly. Although with not a lot of detail, otherwise we will be spending all of this semester talking about memory scheduling. And we don't want to do that necessarily. Even though it's a really important topic, there are many, many important topics that we're going to cover. Okay, and this is important. This is one of the reasons why TCM is not really implemented in existing schedulers. So PowerBS, for example, a lot of the principles are implemented in various different schedulers, like some of the SoCs Samsung has in mobile systems, especially batching, for example, is very useful. But this is much more complex. Okay, so the goal is to actually reduce the complexity a little bit and have a different kind of thinking. Can we actually do that? And that brought us to the Blacklisting memory scheduler. I like the name of this. And eventually we named this Bliss. We've achieved Bliss in memory scheduling finally. And we don't have a paper after that, actually. But we'll see. I think this is a lot easier to implement, and you will see why. Basically, we've covered a lot of application-aware or thread-aware memory schedulers. And they operate in this way. Basically, they monitor application or thread behavior, and after monitoring, they rank the threads in some way. And they enforce the ranks after that. So it turns out this enforcing the ranking is not that easy, basically. Well, first of all, ranking itself takes some amount of time, monitoring takes some amount of time, and enforcing the ranking actually affects your critical path and the complexity of design. Critical path, you can always optimize for the critical path by pipelining and doing things in an overlap manner that increases your design complexity and circuit complexity. So if you do the dumb thing, your critical path will increase in this case. So we want to actually have a scheduler where you could actually do the dumb thing and your critical path will not increase that much. So enforcing the rank, as you can see, there are a lot of comparisons that you need to do, and you need to figure out the highest rank application ID over here, right? And also enforce the relative ranks also, not only the highest rank. Okay, so full ranking across applications or threads increases critical path latency and area significantly to improve performance and fairness. So let's take a look at the schedulers again conceptually after all of this. So there are three axes that we're going to consider now. It's not only performance and fairness, but it's also simplicity. And going this way is better. So ideally, you would like to be there. FR-FCFS, the hit-first scheduler, puts you there. It's very simple, but fairness and performance are lacking. So that's application unaware. Right. The three schedulers that we've discussed have this sort of characteristics, again, based on some workloads. Right. Clearly, this is workload dependent also, but in the grand scheme of things, clearly these are not simple. In fact, if you look, PowerBS is the most complex one over here. Atlas is a simpler one. And TCM is still not bad. But some components of PowerBS are actually really simple. Okay, basically these are application aware, and they all do ranking. And they're all complex. So the key question is it essential to give up simplicity to optimize for performance and fairness? And the answer is no, at least for some workloads, for the workloads that we've evaluated. Without ranking, you can achieve high fairness and high performance, maybe not as high as some of them, but at the benefit of very high simplicity. And the idea, there are two key observations that lead to this. One is, you don't need to rank between every single thread. You can group them. It's sufficient to separate the application into two groups rather than do full ranking. Basically, you still want to monitor. Instead of ranking, we're going to form two groups, vulnerable group and interference-causing group. And we're going to switch, we're going to determine membership in these groups very, very fine-grained. So if something is interference-causing, it's not going to be interference-causing for a really long time. We're going to keep track of it at a fine grain. So let's assume that you found that these are vulnerable and these are interference-causing. You're going to rank the vulnerable ones over the interference-causing ones. So this is much simpler than forming a full ranking, clearly.
It was similar in in the earlier that you classify into non-intensive and intensive. So yes. What's the difference between?
Yeah, the difference will be how you form the groups, basically. Yeah, okay. Yeah, we'll see that.
Conceptually, it looks.
Conceptually, yes. Conceptually, it's very similar, actually, going back to that part of thread cluster memory scheduling. But we'll use it. We'll do it in a fine-grained manner. So if you actually read the thread cluster memory scheduling paper, or if you remember my quantum-based operation, that had the vulnerable and interference-causing groups as determined, or latency-sensitive and bandwidth-sensitive clusters determined across a large number of cycles. Mm-hmm. Here we're going to make it much shorter cycles, and we're going to use different metrics. Oh, this is a mean of this is I don't know why this is operating on its own. So how do you classify applications into the groups? That's the key difference, basically. The second observation, and we want to be simple in that also. We don't want to track many metrics. And it turns out serving a large number of consecutive requests from an application causes interference. And this is a good predictor of the future also. So the basic idea is to group applications with a large number of consecutive requests as interference causing and blacklist them. So this is, if you will, this is the blacklisted group. And you blacklist them and you deprioritize the blacklisted applications. And you clear the blacklist periodically at a very fine grain, such that they have another chance, basically. If they cause interference again quickly, they will be blacklisted again quickly. But if they don't cause interference again quickly, they will not be blacklisted. So if an application has some period where it's causing a lot of interference, it will be blacklisted, and it will soon be not blacklisted after that. And it can, if it's really not causing interference at that point, it will be prioritized. So that fine-grained behavior actually adds a lot of benefit to the scheduler. Lower complexity is clear. This description itself is not complex, as you can see. And you get finer-grained grouping decisions. As a result, you get lower unfairness and high performance. You can adapt to the behavior, changes in the application behavior, much more easily. That was actually a problem we did not talk about in many of the previous schedulers. Like, they do not adapt to the changes in the application behavior very well. You have these time quantums, and if an application changes behavior a lot within the time quantum, you're not adapting to it at all, right?
So were there any use cases for them that there was some application for them this time adapting?
Yeah, absolutely. There are many cases where things change a lot in the fine grain. Okay. Basically, you can actually get highest performance in these workloads again. Again, a lot of these results are workload dependent. That's true for many, many optimizations that we have in systems. It's close to fairest. It's not the fairest scheduler. So some others are fairest. And it's close to simplest. It's not the simplest scheduler also again. It's closer to ideal, basically. So let's take a look at the performance and fairness trade-off. You can read the paper for more detail. But basically, again, for these workloads, the results may look a little bit different. I don't know why these are not marked very well. But basically, it's, again, closest to higher performance. Well, in this case, it's high performance, actually, for these workloads. But it's not the fairest. So the fairest schedulers are here. For example, PAR-BS is still the fairest scheduler compared to the previous. In this case, TCM is not the highest performance scheduler. Well, it is, actually, in this case. Okay, I take it back. But it's not the fairest scheduler for these workloads. Okay. I said that. So let's take a look at complexity. And this is complexity, take it with a grain of salt. This is not very optimized. As I said earlier, if you do the dumb thing, this is what the critical path you would get. Basically, ideally, you want your critical path to be 0 and your area to be 0, right? Clearly. And FR-FCFS and FR-FCFS plus cap gets you here. That's PAR-BS. If you don't optimize it well, your critical path is much longer. Now, if you optimize it, the critical path, your area starts increasing. So you can actually get to some point over here in PAR-BS, perhaps, low critical path and high area. This is Atlas. That's thread cluster memory scheduling. So they're all over here, basically. You need to optimize them to reduce the critical path, meaning to make the scheduling decisions more quickly. But if you... Oh, how did this come about? Okay. But if you look at... blacklisting, it's over here. So it reduces the critical path significantly compared, well, this is the area significantly, and it gets close to the area of FR-FCFS. And it reduces the critical path significantly. Again, it gets close to the critical path of FR-FCFS. But take these with a grain of salt. You can always optimize the critical path by increasing the area a lot more. There's an interesting trade-off here. Okay?
Critical path really necessary, because if you are taking a decision like after a long interval, like let's say 1,000 clock cycles, and basically if you take a decision later on, so it doesn't matter.
So this is the decision of scheduling a given request. So it's really the critical path. So you really need to do it within the bus cycle. So you do have a requirement. Actually, it's not shown here, but there's a particular clock latency you need to achieve to satisfy the requirements of DDR2 800, for example, versus DDR2, DDR3, depending on the frequency that you have on the bus. And the paper analyzes that. But I don't want to harp on it, because you can really optimize all these schedulers to fit in the critical path. It really is about the effort and the area cost. Okay. And you can read this paper. Well, for more detail. Okay, and that's the bliss, basically. So I believe this is more implementable, and I think this is really a fascinating area still. It's not clear if there are better schedulers to be found after this, and they all have their trade-offs. But there's more, there's a lot more to be done in this area. If you're interested, definitely let me know. Okay, let's look at some other systems. So far, we've been assuming a multi-core system with cores being the same, right? But if you become heterogeneous, things become a little bit different. And I'm not going to go into a whole lot more detail in these schedulers, but I'll give you an executive summary over here. So if you have a heterogeneous CPU and GPU system, it turns out that GPU system is very, very bandwidth intensive for the reasons that we have figured out when we looked at the GPU, right? It has massive parallelism. As a result, it has massive memory parallelism as well. So you need large request buffers. And it turns out that these existing monolithic application-aware memory scheduler designs, not Bliss, this was actually developed before Bliss, they're hard to scale to large request buffer sizes. So the solution is, in this case, is stage memory scheduling. And there are multiple concepts over here that could be useful in the design of a memory scheduler, maybe not in this particular form. But the idea is to decompose the memory controller into 3 simple stages. First stage, you form batches to maintain row buffer locality. It's a different way of looking at memory scheduling, basically. Instead of prioritizing things that are hitting in the row buffer, you already form the batches such that those batches go to the same row together. In fact, you could encode the batch in a different way. You could, for example, say, oh, this goes to row X, and I want these cache lines from row X. You basically send an address and a bit vector to the memory controller, and you do the scheduling using that, as opposed to sending each request one at a time, right? So that's the first step. The second step is you basically schedule across these batches. You have many batches, some coming from CPUs, some coming from GPUs, and you try to reduce the interference between applications. Here, you're application aware. Again, how do you do that? We're not going to go into a lot of detail, but I'll give you an example. And the third one is the thing that you really want to keep simple. And that's really the DRAM command scheduler. Basically, you have all this information. Scheduler makes a decision over here, and it feeds commands into the lowest level of the queues. And the goal of this is just to issue a request to the DRAM. And it turns out this is simpler and more scalable compared to application-aware schedulers, not Bliss again. This is older. And it provides higher performance and fairness in a heterogeneous CPU GPU system. Let's take a look at the system. Basically, the purple requests over here are coming from the GPU. Even this is less exaggerated, actually. We could have exaggerated this more. If you have a CPU GPU system integrated and accessing the same memory scheduler, which is true in many integrated CPU GPU systems today, you have a problem because GPU actually hogs the memory request buffers, and the paper has analysis on that. So what's the key idea of stage memory scheduling? Basically have per, let's say, core or per groups of cores, queues, and form batches. And the idea of batches, well, I don't show the batches here, but basically you combine requests that go to the same buffer, same row buffer. So this is going to have a large batch, for example, because GPUs tend to generate a lot of requests that are streaming, right? The next step is batch scheduler, and the next step is the very simple DRAM command scheduler. So how do you form the batches? Basically, that's the idea of batch formation. You delineate things that go to the same row buffer. That's why GPU has a high. This is a lot of requests that go to the same row buffer. Okay? And the next stage considers the sizes of the batches. So, for example, it could decide to prioritize this little thing over here because, again, to improve the performance of this latency-sensitive core, right? As opposed to prioritizing this GPU. And the third stage is command scheduler. So in this particular paper, the batch scheduler has multiple policies, and I believe this is really the direction that things should go forward. So it basically schedules shortest job first sometimes, which means that it schedules the shortest batch first. And when you schedule the batch, basically you fill in the DRAM command scheduler with a bunch of commands that are part of that batch. So it's easy for the DRAM command scheduler just to schedule those after that. So this part is really simple. The hard part is actually this one. How do you design that? And sometimes you may actually choose a round-robin policy and go round-robin across these queues. maybe that's when you want to optimize for fairness, right? Or maybe when you want to when you figure out some application is not meeting its requirements, which you may know with the GPU, you actually start taking things out of that particular queue. Again, in the, this work actually has a probabilistic way of switching between these different policies, which probabilistic scheduling is actually good in many cases. People have actually shown that in operating system scheduling also, so that different applications get their proportional share. Anyway, I'm not going to go into that more than what I just said. But let's take a look at the complexity. It turns out, even compared to a row hit first scheduler, this consumes much less area and much less power. So row hit first was the simplest scheduler that we've talked about so far. Well, simplest scheduler is really not scheduling, first come, first serve. But row hit first is a little bit more intelligent, of course. So you get much less area. And the reduction really comes from this monolithic scheduler becomes stages of simpler schedulers. Each stage itself has a simpler scheduler, considers fewer properties at a time to make the scheduling decision. And each stage has simpler buffers, FIFO instead of out of order. You could actually make even the first stage FIFO while losing some row buffer locality. And each stage has a portion of the total buffer size. Buffering is really distributed across the stages. So it's really a distributed scheduler. It's a multi-level scheduler. And I'll give you very quickly performance results. So this is, now your performance evaluation becomes interesting because you have a CPU GPU workload. In this case, we don't have an integrated workload. It would be very interesting to see what happens if you actually run the same workload that is partitioned across the CPU and GPU. But it's really a multi-programmed workload. You're running something on the GPU and something on the CPUs. And GPU may have some importance. Right? If the GPU is really important, you want to prioritize the GPU. If the GPU is not important, you want to deprioritize the GPU. And this is what the for some performance metric, this is the performance that different schedulers get. So as you can see over here, the performance is really high over here because you're prioritizing the GPU, and GPU inherently has very high performance, right? So the best previous scheduler is different depending on what you want to optimize. So if the GPU is important, for example, first ready, first come, first serve is not a bad scheduler because it's really optimizing for row buffer locality, which the GPU has a lot of. But if the GPU is not important, then the latency sensitivity of the cores start mattering, and Atlas becomes the best scheduler in terms of system performance. And there's a little portion over here where thread cluster memory scheduling is actually the best scheduler among the ones that are evaluated. So this gives you in one picture that no one scheduler is the best, depending on what you place importance on. So SMS, at least in this context, turns out to be better than all of the previous schedulers, and at least the same as some of the FR-FCFS scheduler over here, because it really adapts to the characteristics of the of this weight over here. And if you want to take a look at how it does, you need to look at the paper. Basically, it uses the weight to switch probabilistically between the shortest job first and round-robin scheduling policies to optimize for fairness and performance, right? So here, the weight is very low. Here, the weight is very high. You're most of the time prioritizing the GPU, actually. Here, the weight is very low. You're not prioritizing the GPU. You're actually using the shortest job first policy, which is very similar to Atlas. Okay. So for more detail, you can look at that paper. I'll very quickly describe a little bit more because the complexity increases as the system becomes more heterogeneous. Remember, I showed you a version of this picture in the past. And this is a modern SoC, essentially. You have CPUs, hardware accelerators, and some of these may be GPUs. Why does it have a mind of its own? It's moving by itself. Okay, let's see if we're going to be able to fix this quickly. Is it slideshow? Yeah. Don't use timings. Don't do anything, basically. Okay. Okay, that's better. Okay, so in modern systems, actually, you have many hardware accelerators. It could be a video encoding engine, for example. It could be a GPU. I don't know, it could be a machine learning accelerator. It could be many things today. And this is going to increase. It's not going to reduce going forward. And the main memory is shared between CPUs and hardware accelerators, so you have interference. And these all have different requirements. a video decoding and encoding engine has a different requirements from an image processing engine, has a different requirement from a machine learning inference engine, right? So how do you do this actually? So you really need to schedule requests from both CPUs, which may also be important, and hardware accelerators to mitigate the interference. And some of these are very predictable. The access patterns of some of the hardware accelerators are actually very, very predictable. And if you read the paper that I'm very briefly going to gloss over or talk about, it talks about some of these hardware accelerators, like image processing accelerators. So if you know your memory access pattern really well, you may actually figure out what's the worst case execution time of that access pattern, and you may actually try to minimize that. Okay, so the summary of this scheduler is hardware accelerators and CPUs share the same memory subsystem and interfere with each other. The goal was to design a memory scheduler that improves CPU performance while meeting hardware accelerators' deadlines. Of course, these may have deadlines also, so how do you handle that is the next step perhaps. So the challenge is different hardware accelerators have different memory access characteristics and different deadlines, which current schedulers do not actually smoothly handle. So for example, memory-intensive accelerators and accelerators that have long deadlines significantly degrade CPU performance when they become high priority. So the idea is a lot of these memory schedulers that take into account hardware accelerators keep track of the progress of an accelerator. How much have you made progress? So have you made enough progress in terms of the servicing of the request to satisfy a frame rate, for example? If you have not, prioritize the accelerator. And if the deadline is long, like the deadline for processing a frame is long, and if the accelerator is memory intensive, they become high priority a lot because they make slow progress, and if there's a lot of interference in the system also. So it's important to handle them well. And there's no perfect way of handling, actually. This is memory scheduling in the end. In fact, there is always a question of what is the ideal benefit that you get out of memory scheduling. That's really an MP hard problem in the end because workload characteristics change and a lot of things change. So you really need to simulate that ideal. But even how to simulate that ideal is not known at this point. Of course, you have a very high ideal upper bound, which is you have absolutely no interference in the system, right? And you don't maybe have any anything other than data bus conflicts. But even data bus conflicts is an interference. So ideal is very hard to get. That's why we're going to use a lot of heuristics. And that's why we've been using a lot of heuristics. So on the other hand, accelerators that require very short, very quick response sometimes miss their deadlines, even though they may be given high priority. So you have very different types of accelerators. Something that requires a very quick response, something that has a long deadline. It needs to render this frame for a long time, but it still needs to, it's very memory intensive, and it still has some performance requirements. So they actually interact differently with the CPUs. So one solution is the scheduler that I'm going to very briefly describe. The idea is to prioritize the hardware accelerators over CPU anytime when the hardware accelerator is not making good progress. So instead of waiting until it starts missing its deadline or some threshold, you try to keep it to a balanced progress. So you want to have a progress level you want to always satisfy. And you want to prioritize them if it's not making good progress early on, such that you don't prioritize them at the last moment when it really, really needs to meet its deadline. Okay, and you need to use application-aware scheduling. Unfortunately, we're back to the application-aware scheduling because this is really hard. So for example, a scheduler like Bliss is not a good fit perhaps over here, right? It's very simple, but the requirements of a system like this may not always demand Bliss. Bliss may have a role to play in part of the system, but maybe not in this case when you're prioritizing between hardware accelerators and CPUs. Okay, so you can look at the results. Basically, the results look okay. You can improve CPU performance while meeting the deadline ratio, while meeting all the deadlines for the hardware accelerators. And if you want to experiment with it, actually, a lot of these schedulers are online. Actually, you're going to build a scheduler for one of your labs that's coming. But it's not going to be as complex as any of these, frankly. Okay, so let's take a look at this again. The goal in a heterogeneous system is to design a memory scheduler that meets the GPUs and accelerators frame rates or deadlines while achieving high CPU performance. The basic idea is to cater to the different requirements. And there's really no other way, in my opinion, to do this. If you come up with another way, just let me know. different applications and different accelerators have different requirements. You need to track progress of different agents and prioritize accordingly. And how do you keep track progress is basically really application specific at that point, right? You need to know the deadline, and you need to know how much progress you made, how many requests you've serviced. So for example, for a 30 frames per second request rate, if you know how many requests that you need to service to achieve 30 frames per second, you actually can calculate how many requests you have, and you need to service in a given time period. And if you're not satisfying that many requests in a given time period, proportionally, as you scale down the time period, then you can say, oh, I'm going to prioritize this accelerator, right? So you need priority to meet the deadlines, and worst case prioritization is not always the best, meaning you actually have a deadline, and you schedule all the requests right before the deadline. That's really not good, because you may actually have some other accelerator requesting something, or some CPU requesting something at that point. You may actually delay the workloads, because that requires worst case prioritization for all of the agents. Now that's a really bad worst case, actually. That's really, so if you look at a hard real-time system, they operate based on the worst case requirements, but their systems are actually much simpler. For example, if you have an anti-like ABS system, right, anti-like brake system. How do you design the microcontroller that meets the deadlines? Well, they're not running next to a GPU or a CPU, right? Hopefully you have a microcontroller that actually is customized to meet that deadlines, and they use actually memory schedulers that are optimized for that worst case. They're very rigid. As a result, they're not very high performance. They're low performance, but they meet the deadlines, because you know the deadline and you can customize your memory controller for it. But of course, there's talk about a lot of car companies want to consolidate costs. They actually want to use multi-core systems to do that all sorts of processing that's going on in the car. Then the question is, how do you actually guarantee that your ABS system is working while your DVD player is also playing music, and maybe you're taking pictures, and you just don't want to crash in the meantime, right? So those problems may actually appear again, because these little microcontrollers are not they're not only harder to manage. I'm not going to suggest that they're costly, but they pose a reliability problem, actually. If you have so many electronics in a system, you have a reliability problem. Having a single big, like a car-wide data center, let's say, can actually enable you to be more reliable, assuming you can actually guarantee that it works correctly. Okay, anyway, I've digressed a little bit, but I think that's those are some of the things that may be coming up into the future. Okay, so basically, you prioritize the accelerator not at the deadline, but before, when they're not on track to meet the deadline. So you distribute the priority over time. This mitigates the impact of accelerator on CPU cores requests. And how do you do that? You need to read the paper. Actually, the paper is not enough, because it really depends on the system that you're designing. You need to know your accelerator. You need to know its progress rate. And these different accelerators are also different. Long deadline accelerators are more likely to meet their deadlines because the deadline is long, whereas short deadline accelerators have very little time to meet their deadline, so any kind of interference actually destroys their performance. As a result, it's important to schedule the short deadline accelerators based on worst-case memory access time. So compute the worst-case memory access time, assuming all types of interference, and schedule them as early as possible such that you meet their deadlines. Because they're probably important accelerators, like an ABS, for example. You want very quick response time, right? Okay, and also, clearly, we've seen that not all CPU cores are equal, right? Some are more vulnerable to interference, some are less vulnerable. You want to prioritize the accelerators over memory-intensive cores to ensure that accelerators do not become urgent. And memory-intensive cores, you can actually you can sacrifice, at least most of the time, if you will, because these are making slow progress anyway, right? So we're going to take advantage of that. Again, these are heuristics. It's a very difficult problem. As you've seen, we've been complicating the problem, right, over the course of this lecture. We weren't talking about hardware accelerators to begin with when we first started with first ready, first come, first serve.
The problem can also be solved by partitioning into different channels, like dedicate for...
We're going to talk about that. Yes, yes. That's a different approach. Right? Now we're talking about this. Yes. Very good point, though. Okay. So the key ideas is you want to distribute priority for hardware accelerators, prioritize hardware accelerators over memory-intensive CPU cores, even when they're not urgent. and so that they don't become urgent in the future, and prioritizes short deadline period hardware accelerators based on worst case estimates. And it turns out this is a good scheduling policy. And this is the scheduling policy. There, you need to optimize it, but this is basically the prioritization order. So priority means sometimes they become urgent because they're not meeting their deadlines. So short deadline period hardware accelerators that's not on track for meeting its deadline, it gets prioritized. The next one is long deadline period hardware accelerators that is not meeting its deadline. Next one is memory non-intensive CPU workloads. Of course, there could be more optimization if you have more knowledge about what that CPU core is executing, right? In fact, here it might be a good idea to give that information to that memory controller. And here, which one do you prioritize? It turns out switching probabilistically, again, might be a good idea because sometimes you don't know what decision is the best. Right? And this one is the lowest priority over here. Short deadline period hardware accelerators that are on track to meet their deadlines because you scheduled them based on the worst case execution time, right? You computed the worst case execution time because it has regular memory access patterns, and you said, I'm going to schedule it based on this. Okay, and that's the paper. Okay, I think that brings us to a very good point to stop, and I have time to take a couple of questions. I've covered a bunch of schedulers. Are these interesting? Yeah? I think a lot of these principles appear actually in many, many other places in systems also, because scheduling is very, very commonly employed. So hopefully, maybe you can take some of the principles and use them, or maybe you can design the best scheduler for this in the future, which is really not an easy problem. It's a hard problem, but hard problems are the ones that make the difference. Okay, then we should part today. I'll see you tomorrow. Maybe we'll start here, or maybe we'll start with something else. I've given you a glimpse of the predictable performance, so I'm not sure if I will start here. Okay, see you tomorrow.